Okay, dear colleagues, hello. It's a great pleasure to be here and to see you all in our conference. I should say, I will just say a couple of words because it is not an opening, not an official opening of the conference. The real opening will take place 4 hours later. But just to say that, to say hello and to say welcome. And I hope Matteo Maestri will also say a couple of words.
Okay, so thank you, Andrei, and a very warm welcome to all of you also from my side and from the side of Politecnico di Milano. And we look forward to the next 4 days with this exciting program. And as said by Andrei, the official opening will be in 4 hours from now. Thank you very much.
Okay, thank you, Matteo. So no more long waiting. Let's go, let's start our work. I forward my dispatching rights to chairman of the sections. Good work, colleagues. Thank you.
Right. Hello and good morning to Chem Reactor 24 online conference. I'm very pleased to chair the first section or the first session of this online conference between Revskov Institute of Catalysis of the Siberian branch of the Russian Academy of Science, Novosibirsk, and Politecnico di Milano. And this is Hall 1, Section 1, Advances in Chemical Reactor Fundamentals. And this is the first speaker, and this session goes until 10:40. So I'm very pleased to present to you Dmitry Murzin from ABO, Akademi University, Laboratory of Industrial Chemistry in Finland. I'm very pleased to give up to you. You've got 20 minutes, around 15 minutes, and I will turn on my camera, and then we have enough time for a couple of questions. So it's up to you. Thanks.
Yeah. Thank you very much. It's certainly a pleasure to be here to open this international conference. Actually, it's the Chem Reactor 24, but the international edition of this conference is just 20 years old, and the first conference of that type was held in Helsinki 20 years ago. What I'm going to discuss today will be the apparent activation energy of structure-sensitive heterogeneous catalytic reactions, and I will try to do it in a slightly unusual way, so I will start directly with conclusions. And the conclusions would be like this, that the apparent activation energy depends on the size of clusters or metal nanoparticles, and how and why, on why and how, that will be the rest of my presentation. First, we'll have to define what is turnover frequency or turnover number. Actually, turnover frequency is the correct, probably, notation. So it's the number of molecules which reacted per site per unit of time, and then turnover frequency depends on the kinetics, it depends on the concentration of reagents, it depends on temperature. We can have different type of turnover frequency dependence as a function of the size of metal clusters. For structure-insensitive reactions, apparently the turnover frequency doesn't depend on the cluster size, while there could be other type of dependencies that the turnover frequency can decrease with the diameter, or it can increase, or in fact it can also pass through maximum. We are discussing now the turnover frequency of the rate per exposed sites. So apparently the fraction of the surface sites compared to the total number of sites is decreasing as the diameter or the size of the metal clusters would increase. The whole concept of structure-sensitive reactions is certainly not new, and already many years ago, in the review written by Geoffrey Bond, he analyzed dependence of turnover frequency for several types of reactions. As you can see here, there is a plot of the logarithm of TUF versus metal dispersion, which is a reciprocal value of the metal cluster size, and we can see that just changing dispersion, say from 0.5, which means approximately 2 nanometers, to something like that, this size, which probably is 10 nanometers, we can have a huge difference in the turnover frequency, several orders of magnitude. There are several explanations for this type of behavior. One would be related to differences in activities of different surface atoms, which is understandable because they have different coordination. And then one would expect that on face atoms, on corners, or on edges, the Gibbs energy of adsorption would be different. So as it illustrated here, the Gibbs energy of adsorption on edges is not the same as the Gibbs energy of adsorption on terraces. How to go from thermodynamics to kinetics? Here we would use the linear free energy relationship, which tells us something about the relationship between kinetics and thermodynamics, and then the Gibbs activation energy would be proportional to the Gibbs energy of the reaction, where alpha is the linear parameter, and from that one can obtain the famous equation of Bronsted, which actually appeared exactly 100 years ago in his chemical review paper, where Branco proposed the link between the rate constant and then the equilibrium constant. Once again, this is the Polanyi parameter. So establishing the link between kinetics and thermodynamics. So how do we go, where do we, from here, how we can then develop dependence on the cluster size? So if we write an expression for the Gibbs energy of adsorption in a simplified way, considering only terraces and edges, here we have then the fraction of terraces, the fraction of edges, and basically what we need would be to figure out how this fraction of terraces and edges would depend on the size. For that, we will use the approach of two famous Dutch scientists who at some point counted the surface atoms for different type of geometrical shapes depending on dispersion. So if we then go further with the mathematical treatment, we can have that the Gibbs energy of adsorption with proportional to the Gibbs energy of adsorption on terraces. Here we have the fraction of edges, and that will be the difference between the Gibbs energies of adsorption on edges and terraces. From that, we can have an equation for the equilibrium constant of adsorption, and then there will be the next step, the link to the rate constant. One can even go further and calculate not only the influence of or calculate the dependence of the Gibbs energy of adsorption, not only as a function basically of the size, but also of the shape. There we should go a little bit more in depth on the type of metal clusters. For instance, for the cube, it's possible then to write an expression of that type. And then for the cubo-octahedron, then it will be a little bit more complicated. So here, this fraction of edges, corners, and terraces can be precisely calculated through this parameter m, which is a number of atoms lying on a particular edge. And then from that, we can have a relationship between this m and the diameter of the cluster. It's even possible, so where is the size dependence, you might ask? For the cubo-octahedron, it's even simpler. The treatment as the fraction of edges to the total number of edges and terraces can be quite easily approximated to the reciprocal dependence on the cluster size. From that, we can go to the kinetic equations, for instance, for the two-step sequence, where we have adsorption of a certain compound forming an intermediate, and then in the second step, this intermediate will react with the second reactant. We can derive a very well-known equation for the stationary kinetics, where these omegas would be frequencies of steps. Then the next step will be to write explicitly expressions for the dependence of rate constants on the diameter of cluster. And here I have expressions for the so-called adsorption type of steps. Here will be the dependence of the desorption steps. So what we have here will be then the so-called pre-exponential factor. Here I have Polanyi parameters for different steps. That will be the diameter of the cluster. And this parameter reflects then the difference between adsorption of edges and terraces. Apparently, if this is equal to 0, then we have the case of structure insensitive reactions, and then it means that the turnover frequency will be independent on the cluster size. So with all that, it's possible to develop then the rate equation for the turnover frequency as a function of the cluster size, and actually developing that, one can easily demonstrate that the reaction order will depend on the cluster size. A simplified version where one step is irreversible actually looks pretty simple with 4 parameters, and this type of expression can explain different type of turnover frequency dependence on the cluster size. It can explain an increase or decrease, and even maximum internal frequency. Now, a few words about the apparent activation energy. This is an example of the so-called Facebook science, where some years ago, one colleague put a question on the Facebook asking what is the apparent activation energy of this complex reaction with 3 steps, and it seems that it was a difficult question. So there are some ideas that the activation energy is the maximum barrier of one of the 2 stages, or some comments, and there were quite many, it was suggested that it's the this one is the activation energy. In reality, many of the comments and assumptions which were then put here on the Facebook, they are completely wrong. And in order to calculate the activation energy, what we just need to remember the basics, the definition of what is the activation energy, and then we just we take the logarithm and do a differentiation, which in principle can be done in a rather straightforward way. We take the then this expression, and then basically what we do, we take the logarithm. So we would need then to do differentiation temperature for this term, this one, and actually that one, because apparently the logarithm of concentration would not depend on temperature. This is also relatively straightforward. And then just the first term, the differentiation, will result in this expression where we'll have the activation energy of the first step divided by RT square. The same we can do for the second rate constant. This is a little bit more complicated. Here we have a more complex function, and then we do the substitution. And then by taking the this logarithm and making a substitution, we continue with the then differentiation, and then we can come up with something like that. And then eventually it will lead to this expression, which is also relatively straightforward. So at the end, we will be able then to express the activation energy as a function of activation energy of the first step and of the second step, and that will be some sort of prefactors, which then reflect the frequencies of steps. So it's some sort of average value of the activation energy. It's not the sum of them, and certainly it's not the largest one. So where is then the cluster size dependence? So basically the same approach as I was presenting before can be used to then determine the influence of the cluster size. So what I'm doing now is in this expression for the rate, I will put then the equation which was developed some 5 minutes ago, where I had the dependence of the rate on the size of the metal clusters. Then doing that in a rigorous way, we will have this expression, which looks somewhat complicated. It's possible to simplify that, and I was discussing the 2-step sequence. So if one would assume that the second step determines the overall rate, then the expression can be remarkably simplified, and then what we will get that the activation energy will depend on the activation energy of the second step. Here I have the Polanyi parameter of that step, which is typically approximately 0.5, and here I will have the difference between the adsorption on edges and adsorption on terraces, and all that will be inversely proportional to the cluster size. And then we will see that one can get that equation, which will be in line with experimental data for dehydrogenation of propane. Even more complicated cases can be treated. More recently, this parallel reaction network was analyzed, where furfural can either give through hydrogenation furfural alcohol, or by decarbonylation together with hydrogenation will give furan. So the apparent activation energy, or the expressions for apparent activation energies were derived, and you see the remarkable correspondence of the theoretical predictions with experiments. One can even go further with this type of treatment and analyze what will be the optimum catalyst, or the catalyst with the highest rate. And that was also done very recently. And for the optimal catalyst, it can be demonstrated that the Gibbs energy is cluster size dependent, and those who are interested in looking into the details can check the original paper which was published last year. I think it's time to conclude, and very well on time. I think 1 second is left. So size and shape matters. And then I have the final conclusion that more science should be in social media. Actually, it helps very much to do this type of theoretical development. Thank you very much for your attention.
Yeah, thank you, Professor Murzin. That was very interesting, and I like the social media input very well. Thank you. Yeah, and we have now a couple of minutes in order to answer questions to Professor Murzin in the audience. If not, maybe
you see it's still 6:40. You see whatever is the time, so it's too early. People are still sleeping.
Yeah. So maybe I start as an icebreaker. So in industrial catalysis, we typically have a distribution of the nanosize, of the particle size, size distribution. So how could you deal with that?
Yeah, that's a very good point. And that very much depends on what is the type of turnover frequency. Dependence as a function of the cluster size. You see, if it's structure insensitive, then it doesn't matter. If it's increasing with size or decreasing, it also doesn't matter that much, because it's somehow compensated, the distribution. The important thing would be when you have a maximum, then you will see that when you have a distribution, it will be not as sharp as like that, but you will see that the maximum is somehow smoother. That actually I made this, there is a theoretical paper which I published maybe 7 or 8 years ago, where I considered that case, how the distribution will influence the sharpness of the maximum. Once again, for insensitive reactions, it doesn't matter. And then if you have either increase or decrease, it also doesn't matter. So only for few cases when TUF exhibits a clear maximum, then one should also take into account the distribution.
Can I have a question?
Sure.
Okay, Dmitry, hello. So thank you very much for nice presentation. I have maybe a very general question. How do you think, to what extent the application of the term of turnover frequency is valid in catalysis? How correct is it?
There are two groups of, say, scientists. Some say that turnover frequency should never be used.
That's me.
Yeah, because of the limitations. And we all understand that turnover frequency is something which is attributed to a particular temperature. It's attributed to a particular concentration range. Moreover, as you have noticed, I was demonstrating in one of the slides, the turnover frequency depends even on the reaction orders. So it means that when you compare papers written in different parts of the world, and then colleagues are using, for instance, different concentration domains, turnover frequency can be different. So yes. This is one group of thought. The second group of thought are those people who will force you to report turnover frequency because you cannot publish in Journal of Catalysis without reporting turnover frequency. So this is the crude reality.
Okay, thank you very much.
Right. So I thank you, Professor Murzin, once again.
I will stop sharing this.
For this first contribution to Section 1, Advanced in Chemical Reactor Fundamentals. And now we give up to our second speaker. This is Professor Matteo Maestri from Politecnico di Milano. And yeah, I'm very pleased that you're here. We already saw you a couple of minutes ago in the introduction, but now it's yours to tell us something about KMC, machine learning, and reactor modeling. So,
okay, so thank you very much, Gregor, for the introduction, and good morning, everyone. So today we are going to present you some of the work that we have been doing in the inclusion of kinetic Monte Carlo simulations in computational fluid dynamics, or in general reactor modeling by means of machine learning techniques. So first of all, why we need to deal with this? So first principle-based multi-scale modeling is acknowledged to be one of the key contributors in the detailed analysis of catalytic processes, and can provide some important pieces of information in order to get a fundamental understanding of the process in reacting conditions. However, when we we're aiming at including a detailed modeling and understanding of the reactivity, especially based on kinetic Monte Carlo simulation, we have to face an important problem, which is related to the very different, controlling time step that we do have to consider at the level of the KMC simulation, and the one that we have at the level of computational fluid dynamics. So in the past, my group, but also other groups, for example, our collaborator in Fritzhaber, Professor Kastenreuter, we have proposed as a possible, solution to this problem, the use of a full decoupling of the two phenomena. So basically based on the instantaneous steady state approximation of the kinetics with respect to what happens at the level of the macro scale modeling, we can actually consider all the possible conditions that you can reach at the level of partial pressure of the different reactor and products, tabulate and construct the turnover frequency of the reaction rate in general, and then input this in the CFD simulations. This actually is represented in the scheme over here. So basically, we want to establish and to propose a proper surrogate model that is able to interpret reaction rate data that are basically calculated upfront and beforehand, and later on use these surrogate models in order to deliver in the mass balance equation the proper reaction terms that you need to account in the different conditions. By doing so, and by using this surrogate model, you realize in practice a full decoupling of the dependence between the leading time at the level of the KMC simulation and the leading time at the level of the reactor modeling simulation. There are several possibilities in order to build up and to construct this surrogate model. So we, for example, consider in the past spline or polynomial interpolation, such as Shepard interpolation. However, later on, we got interested in using machine learning techniques in order to build directly a model, a surrogate model for the interpretation of the turnover frequency in the different conditions, in order to provide a very efficient modeling and interpretation and tabulation of this data. So machine learning is indeed able to efficiently tabulate, kinetic, a large amount of kinetic data, and to provide an accurate and fast prediction of these target quantities. In particular, we proposed, by using also some inspiration in collaboration with the group of Professor Dixon, the random forest algorithm, which is a methodology where an ensemble of trees regression trees are trained with the existing data calculated with respect to the turnover frequency. Then we have that the random forest is particularly suited for application like the interpretation of kinetic data, because first of all, is able to deal with the large quantities of data, is also able to provide a very efficient and fast tabulation and retrieval capabilities. So basically, in brief, what we are doing here by calculating, first of all the data under the different operating conditions that we expect to have in the simulation, we train the different trees of the random forest, and then these different trees are considered in order to retrieve the different interpretation and the different queries of the turnover frequency. And in doing so, we are able to construct a continuous representation of the turnover frequency in the different range of operating conditions that we have established upfront. Once you have this continuous representation of the turnover frequency, then you can directly use this information, pieces of information in the reactor modeling. Let me first of all give you some example that I can be definitely more clear than a general introduction to the use of machine learning in this context. So we are focusing now on the CO oxidation on ruthenium oxide 110 facets. So here the system is pretty simple. So we have only basically two different independent variables if we consider a constant temperature for this specific case, which is the partial pressure of CO and the partial pressure of oxygen. What we do is, first of all, we use a kinetic Monte Carlo simulation. Here we actually use the code provided by UCL Zacros, and we computed the turnover frequency for each combination of partial pressure of oxygen and partial pressure of CO. And in the end, we are able to have an example of pair of CO and oxygen and the corresponding turnover frequency. We use this set of data in order to train the random forest algorithm. And by doing so, we are able to construct now the continuous representation of the full value of turnover frequency in the boundaries, in the range that we have established up front of CO partial pressure and oxygen partial pressure. If we now compare the kinetic Monte Carlo simulation value and the one which is obtained with the continuous representation based on the machine learning algorithm, we can see that we have a very good fit between the predicted turnover frequency by the random forest query and the turnover frequency calculated directly with the kinetic Monte Carlo simulation, with the advantage that now we have a consistent speed up factor. In fact, even with this very simple case, we have that the random forest query is basically costless in terms of time, whereas if you would have realized directly on the fly the calculation of the AKMC coupled with the reactor simulation, we would have a consistent overhead in terms of computational time. So in this case, the time is actually, if you want, negligible, even in the case of KMC. But however, if you think this in the context of a complex reactor simulation of even computational fluid dynamics simulation, you can actually appreciate, how important it is actually to have this surrogate model in order to speed up the calculation at the level of the reactor simulation. However, the overall problem is based on the disposal of some training data that in principle can be quite important in terms of computational time required. So let's say that if I have a much more complex cases, for example, 4 or 5 independent variables plus the temperature, and I need actually to consider all the different possibilities in the range of operating conditions that you have established up front, you can easily run into the problem that you have such an amount of data to calculate at the level of the KMC that becomes, even at front, basically completely unfeasible. So you should actually consider months of calculation before actually you are able to use this data in order to train the random forest algorithms. Moreover, if you're also looking at the case that I already presented in terms of CO oxidation, you can see that our previous choice of having a evenly distribution of the sampling of the different points in the range of operating conditions that we have established, we have a lot of data, for example, here in this range of the domain, that lies in a situation where the turnover frequency is basically completely insensitive to the variation of both of CO and oxygen. So basically you have no rates appreciable rates in this condition. However, you have only a region of your turnover space where actually you would need a lot of data in order to have a consistent, and more accurate representation of the turnover frequency through the machine learning algorithm. So basically, this poses the problem that we need a proper definition of the training point data set in order to improve the accuracy and the efficiency of the approach. And this is actually what we consider and we developed through this adaptive procedure that we publish in the paper over here. So basically, the main idea is in the level of machine learning, we need a lot of data, but this data in the context, in the specific context of kinetics, especially at the fundamental levels, kinetic Monte Carlo simulation, are very costly. So I try actually to, on one side, to maximize the number of points that I need in target region of the turnover frequency space by using an adaptive, sequential simulation and procedure, which is able to directly locate the points where actually they are needed. This is done by an estimation of the first and second derivative of the turnover frequency with respect to the independent variables. And as you can see here, we start from a very, rough number of points equally spaced over the domains. Then we proceed by the calculation of the first and second derivative to evaluate the region of variation of the turnover frequency as a function of the different operating conditions. And by doing so, as you can see here, by increasing the number of points, we start accumulating the different points in the region where actually we have a steep variation of the turnover frequency, whereas in the region of the domain where actually the turnover frequency is basically insensitive with respect to the independent variables, much less points are located where actually they are not needed. As you can see here, by increasing the number of points and by locating the points in the region where we have a strong variation of turnover frequency, we have a consistent reduction of the benchmark error with respect to the direct KMC simulation. And here, basically, we are able to reach evaluation of a number of points not equally spaced, but actually optimizing space with a benchmark error of about 10%, only with 140 points, which is actually of the order of 400 points that we had in the previous equally spaced simulation that I show you in the previous pre-presentation of the kinetic Monte Carlo simulation of the CO oxidation. This here actually is a more detailed comparison in terms of accuracy. So the red dots are the equally spaced, so 400 training points. The black full point is basically the one optimized. You see that both in terms of a representation, for example, of the CO coverage, we do have a very consistent and accurate prediction of the quantity, but with a much less number of points, which results in a consistent gain in terms of computational time required for the performance of the KMC simulations. This allows us, for example, to couple this simulation directly, for example, in computational fluid dynamics simulations. So here, as an example, we couple the previously machine learned kinetic model of CO oxidation at the level of KMC with the virtual reconstruction of the forms, which is actually represented over here. And as you can see here, we can now go from the full description of the fluid dynamics in the reactor, in the complex domain, till the calculation and the prediction of the different distribution of the active sites, which are based on a KMC simulation presented in the different part of the domain of the forms. This actually is a good example of coupling with this effective, decoupling the KMC simulation with the computational fluid dynamics simulation. This actually was presented so far with respect to a very simple case, which are two independent variables and constant temperature, so the case of CO oxidation. But let's see what happens, for example, if we now increase the complexity of our problem. In particular here, I present the application of our methodology to the water gas ship reaction on rhodium. So here we have actually different 5 directions, which are the 4 main species plus the temperature, and we aim to tabulate the CO2 net production rate as an indicator of the reaction rate overall. Here, actually, we compare the average benchmark error between the KMC and the simulation done with the machine learning optimized. And as you can see here, by considering a target error of 2.5%, we are able to, by applying our optimization procedure, to reach the value of 2.5 roughly at 5 K points, located, not equally spaced, located in the domain, which correspond in terms of equally spaced points to roughly, let's say 35 K points equally spaced among the different directions, which is actually an indicator again of the great gain in computational time that we can have with this optimized procedure. So to conclude, I show you that machine learning methods can be efficiently employed for tabulating rates in the context of multi-scale modeling of chemical processes. I also show you the importance of this, especially in terms of KMC simulation, and also the paradox that we have in the application of these machine learning methods in the context. So we need a lot of data to make the machine learning algorithm work well, but on the other side, we need to minimize the data in order to avoid to waste computational time where it's not needed. This is met by this methodology that we have proposed, which is able to optimize the position of the data in the space domain of the turnover frequency. And this allows, in the end, to make a full coupling of the microscale and mesoscale modeling of the kinetic Monte Carlo simulation within the macroscale simulation at the level of reactor modeling and CRT. With this, I would like to acknowledge the funding from the ERC project and also from the Horizon Europe ReactPro project. And I also thank you for your attention, and I would be glad to answer any question you might have.
Thank you, Matteo, for this very interesting talk. And I think we have some time for a couple of questions from the audience. Okay, maybe then I start. So Matteo, which machine learning tool did you use to calculate or to produce your random forest algorithm?
You mean why we use machine learning, or why use a random forest instead of other algorithms?
Yeah, but was it implemented in like a Python code or?
Oh, okay, sorry. Yes, this actually was implemented in Python, and all these code is actually available, some of them on our website and our GitHub. So all the link and detail of the implementation of the code, even of the procedure, you can go to the shape.polimi.it, and then you find a link directly to the GitHub where you can download the procedure. But actually, most of our code are now being implemented in Python.
Mm-hmm, mm-hmm. Okay, then maybe I ask another question. So you use now KMC as a pre-computed model, but I think you can use more or less any model that gives you turnover frequencies. So have you thought about using different sources of input?
Yes, so we actually apply in this context to KMC because actually it's the more time consuming in terms of computation overhead. But the same problem, as you said, for example, can be done at the level of a very complex, even mean field microkinetic model. So what you can do, you can produce your machine learned version of the kinetic model, and in this way, you can provide an efficient and much, in terms of computational time, version of your mean field model. For example, for much complex systems, C1, C2 chemistry, where you have a lot of combination, this actually can result in a substantial improvement of the efficiency of your calculation. I think especially, for example, in real-time simulation, where you want, for example, to perform a quick reactor calculations, but based on a chemistry which is actually grounded at the level of the fundamental information, and then actually you can map these two, possibilities, so a very fast reactor modeling with a very fundamental description of the kinetic model without, considering a reduction and therefore a loss of the information of your kinetic scheme.
Mm-hmm. All right. Yeah, thank you, Matteo, for this great insight. And I think we head over to the next presentation. And microkinetics was a good keyword for that. So this is Raffaele Cheula from Politecnico Milano. He's in the group of Matteo Maestri. And yeah, we're very happy to have you here.
Thank you. Thank you very much for the kind introduction. Can you see my screen?
Yes, that works.
Okay. So yeah, I'm Raffaele Cheula, and today I'm gonna present a work on the unraveling the nature and the identity of the active sites in heterogeneous catalysis via structure-dependent microkinetic modeling. So in heterogeneous catalysis, the structure of the catalytic material deeply affects the catalytic activity. Indeed, catalyst materials can show to the reaction environment different types of active sites which can interact in different ways with the reaction intermediates and also with the transition state. And this affects the kinetic parameters of the microkinetic models. And in particular, if we want to include the effect of like first principle calculated kinetic parameters of heterogeneous catalytic process, we have to first understand which is the structure of the catalyst under reaction conditions, to identify which is the nature of the active sites of the catalyst, and then perform the calculations on those type of active sites. But the structure of a catalyst inside the chemical reactors is not fixed, because the catalytic materials can undergo some surface reconstruction and bulk phase transition, because their size, shape, and composition is deeply affected by the local operative conditions that they experience inside the chemical reactors. And for example, the absorption of a reaction intermediate can induce surface reconstruction of a catalyst nanoparticle, and the diffusion of some reaction intermediates inside the bulk can yield a bulk phase transition. And for example, during the catalytic partial oxidation of methane on rhodium, it has been observed that the reactor bed at steady state conditions is stratified into zones, where in the first zone the catalyst is oxidized and the total oxidation of methane occurs. In the second zone, the catalyst is reduced and the syngas production starts. So two main questions arise in the modeling of heterogeneous catalysis from first principle. The first one is related to the nature of the active sites. So which is the structure of the active sites under reaction conditions? In order to answer to this first question, in a previous publication, we proposed a methodology based on microkinetic modeling, ab initio thermodynamics, and Wolff construction. So with the microkinetic modeling, we derived the composition of the gas phase and the surface inside the chemical reactor. Then with ab initio thermodynamics, we use some DFT calculated data and the composition inside the reactor to understand which is the bulk structure of the catalyst and the morphology of the surfaces. And finally, with the Wolff construction, we calculated the three-dimensional shape of the catalyst and the distribution of the different crystal facets of the catalyst, which determine the nature of the different types of active sites of the catalyst. And the application of this methodology to the catalytic partial oxidation of methane on rhodium allowed to identify the two regions of the reactor in which the catalyst has two different bulk phase composition. Indeed, in the first zone of the reactor, in agreement with the experimental observations, the corundum rhodium oxide is the most stable bulk structure, and this particular structure exposed to the reaction environment three different crystal facets, whereas in the second zone of the reactor, the catalyst is metallic, and it exposed to the reaction environment five different crystal facets, which are the facets showing the active sites for the developing of the reactor. However, once we know which is the structure of the catalyst and which are the possible active sites on which the catalytic reaction occurs, another question rises, which is which active sites give the major contribution to the overall reaction rate. So in order to answer also to this problem, we derived and implemented and applied a novel methodology for the identification of the identity of the active sites which give the predominant contribution to the overall reaction rate. The first steps of the methodology, called structure-dependent microkinetic modeling, are the ones of the methodology that I already shown. So with ab initio thermodynamics and Wolff construction, we calculate which is the structure of a catalyst under a reaction condition, and we identify the nature of the active sites by selecting the crystal facets of the catalyst exposed by the catalyst. Then, once we selected which are the crystal facets of the catalyst that are present in the reaction condition, we derive microkinetic models for each of those facets. And with an adjusted band calculation and transition state theory, we calculate the kinetic parameters for each active sites. Then we implement the microkinetic model, which contains the information of the structure of the catalyst for the calculation of the composition evolution inside the chemical reactor, and we back input this information for the calculation of the structure of the catalyst. This methodology allows to identify the identity of the active sites which give the predominant contribution to the overall reaction rate by accounting both the activity of the active sites, so the reaction rate per active sites turnover frequency, and abundance, so the structure and the distribution of the active sites. We applied this methodology in the context of the water gas shift and reverse water gas shift reactions on rhodium. In particular, for this system, previous experimental studies showed reaction orders which suggest that the two reactions occur with different elementary steps, which are the rate controlling steps of the reaction. So in order to achieve some fundamental atomistic information of the catalytic processes, we derived a microkinetic model based on first principle DFT calculations, which contains the information of 23 different elementary steps on 5 different crystal facets of rhodium, which are the ones exposed by during the reaction. The model is based on transition state theory on the mean field approximation and contains the information of the lateral interactions of the reaction intermediates with the carbon monoxide. We used the microkinetic model to simulate the experimental setup previously shown in the experimental works previously analyzed. And in particular, we used the finite difference integration, in which at each point of the integration, we calculated the reaction rates of the elementary steps of the microkinetic model by accounting both for the intrinsic activity of each active sites and also the abundance of the active sites. The activity of the active sites is given by the turnover frequency, so the reaction rate per active site, whereas the abundance is given by the extension of the different of the surface area of the different crystal facets exposed by the nanoparticle catalyst during the reaction. As the Wolf construction needed in the model is a size-independent methodology, the model has one degree of freedom, which is the nanoparticle diameter. And we used that particular parameter to fit some experimental data. And with just one parameter fitted and all the other data extracted from density functional theory calculations, we were able to reproduce very well some experimental data. Then, once we calculated which is the microscopic behavior of the system, we analyzed what is happening at the nanoscale. In particular, we analyzed the conditions far from equilibrium. And during water-gas shift reaction, we calculated which is the identity of the active sites that dominate the catalytic transformation. In these conditions, we found that the crystal facet 311 was giving the highest turnover frequency, so the highest turnover reaction rate per active site. However, the crystal facet 111 is far much more abundant than the other facet. And when we calculate the productivities of the different crystal facets by accounting both the activity and abundance, we found that the crystal facet 111 was dominating the conversion of carbon monoxide and water to CO2 and hydrogen. This microkinetic analysis allowed to derive also the reaction path of the system and to identify the rate controlling step of the reaction, which is the dissociation of water. When we compare the reaction orders calculated with the microkinetic model and the experimental ones reported in the literature, we found a very good agreement. Moving now to the reverse water-gas shift reaction on the same catalyst, far from equilibrium. In this case, we found that another different crystal facet was governing the transformation of the reactants to the products. In particular, the crystal facet 100 was shows very high turnover frequency and also a correspondingly high productivity of the reaction. And on this crystal facet, we identified the CO2 dissociation as the rate determining step of the reaction. Also, in this case, when we analyzed the reaction orders calculated with the microkinetic model, and when we compared with the experimental ones, we found a very good agreement, confirming our results. So if up to now we analyzed the system far from equilibrium, what happens when we approach the thermodynamic equilibrium of the gas phase? At the thermodynamic equilibrium of the gas phase, the reaction rate approach 0. However, in the immediate two sides of the equilibrium, so while approaching the equilibrium with the water-gas shift reaction and while approaching the equilibrium with the reverse water-gas shift reaction, we achieve the same behavior of the catalytic system. Indeed, close to the thermodynamic equilibrium, we have that the composition of the catalyst, the coverages on the catalyst, and the reaction rate, the proportionalities of the reaction rate converge to the same values because of the concept of the microscopic reversibility. In conclusion, ab initio thermodynamics, Wolff construction, and microkinetic modeling can be used to describe the morphological changes of catalyst materials under a reaction condition. The nature of the active sites can change during the reaction, and its knowledge is fundamental for the inclusion of first principle techniques in microkinetic analysis. The identity of the active sites is determined by both the activity and the relative abundance of the different possible active sites of the catalyst, and it can be obtained by a structure-dependent microkinetic model. Finally, the application of the structure-dependent microkinetic model of water gas shift and reverse water gas shift on rhodium allowed us to identify the preferred reaction path of the catalytic system, the rate controlling steps, and to interpret the experimental reaction orders. With this, I would like to thank you for your attention.
Yeah, thank you, Raffaele, for this nice talk. And I think there are this time a couple of questions from the audience.
I have a question, actually a couple of questions. Can you use this approach for the rational catalyst design? And if yes, can you imagine to have in the reactor different type of catalyst to optimize each step of the reaction?
Okay, so when you say catalyst design, you're talking about bimetallic mixtures of catalyst, or also, for example, production of a particular shape of the catalyst, which can produce, for example, some selective products.
Exactly. For your cases, it's the second. So if you can really use directly your results to produce this catalyst.
Okay. So I think in that case, you should model some preparation procedure. And like we did some works on the modeling of the shape of nickel oxide nanoparticles in molten salt synthesis. Yes, so you can use the same approach also to analyze which would be the shape of the catalyst in some preparation conditions. However, what you would expect, especially for metallic catalyst, is that once you catalyst with a particular shape and you raise the temperature, sometimes the shape of the catalyst would achieve the thermodynamic one. So even if you model the thermodynamic shape during the preparation procedure to have some particular exposed crystal facets, when you perform the reaction at some like high temperature, especially, you would transform also the catalyst. You would observe some catalyst deactivation. If you work at ambient or like low temperature, sometimes you don't have this problem, and especially this problems are not shown by metal oxides, which show usually higher cohesive energy, and therefore they're less able to reconstruct during the reaction. Yeah.
Okay, thank you. But in principle, can you imagine of having different type of catalyst in your reactor to, for example, have first the oxidation and then the reforming of methane?
Okay, so yeah, you can imagine, and in particular, during the partial oxidation of rhodium, in particular, what has been observed during some experimental observation and also some theoretical studies is that the thermodynamic shape of the catalyst and the composition changes during the reaction, because along the catalyst bed you have a change of the of the pressure, partial pressure of the gas species, and therefore the chemical potential of all those species. At a different chemical potential of the gas phase induce also reconstruction of the catalyst. And for example, it is hard to understand if you can manage, if you can work on like the definition of those particular compositions of the catalyst, because usually you cannot decide which will be the thermodynamic equilibrium shape and composition of the catalyst, but it will be the system which will adapt and form different particle structures.
Okay.
Perfect. Thank you. Nice work. Thank you.
Thank you, Emanuele and Raffaele, for this nice discussion. But due to our limited time frame, I think we once again thank you, Raffaele, for this nice talk. And we go to the next speaker. This is Daniel Branco from Flemish Institute of Technological Research in Meaux, Belgium. And the floor is yours.
Thank you. Okay, I'm only seeing my presentation here. I'm going to talk about the research that we've done about invariant expressions in chemical kinetics. This is a joint work with the University of Ghent and University of St. Louis in the United States. Invariant expression is a function of state variables that remain constant during the course of the chemical reactions, also during the dynamic changes that happen during the chemical reaction. We know some, and they are related to mass balance. They are element conservation and stoichiometric relations. For instance, for this reaction, these are the invariant expressions related to element conservations. The total amount of hydrogen and oxygen remain constant. And the stoichiometric relationships are these ones here. For this simple reaction, A goes to be the reversible reaction.
Unfortunately, we cannot see your presentation. Could you please share the screen?
Sorry, I didn't do that. Share screen. Now?
Now, yes, we can see. Thank you.
Okay, I will start again.
Full screen.
Yes, full screen, please.
Now you can see it.
Now it works, yeah. Thank you.
Thank you. So, invariant expression is a function of state variables that remain constant during the course of the chemical reactions. So far, we know some invariant expressions related to mass balances. These are the element conservations and stoichiometric relationships. For instance, for this reaction, these two are the equations, the invariant expressions related to element conservation. The total amount of hydrogen and oxygen remain constant. And the stoichiometric relationships are these ones here, related to the rate of the composition and formation of water. But let's start from a simple chemical reaction. A goes to B. We know that the total amount of A plus B has to remain constant. And from the stoichiometric relationship, that we know that the rate of disappearance or the rate of the composition of A is equal to the rate of formation of B. We found another type of invariant expression, an expression that remains constant during the whole reaction, and we will call them ABA type invariants from reciprocal experiments. Let's suppose that we make a first experiment starting from pure A, and we record the concentration of A as a function of time and the concentration of B as a function of time. These two concentrations have the subscript A, indicating that I started from initial concentration of A and no B in the reactor. And then I make a second experiment, the reciprocal experiment. I will start from B this time, and I will record the concentration of A as a function of time and the concentration of B as a function of time. AB and BB indicate, the subscript B indicates that these two concentration profiles were obtained from a reactor feed with only the substance B. It happens that these two concentration profiles, AB and BA, are proportional and equal to the equilibrium constant of the reversible reaction. This equation holds not only at equilibrium, the ratio BA over AB is equal to the equilibrium constant. It's not only valid at equilibrium, but also during the initial stage of the chemical reaction at any time. And this is interesting, and because this has interesting, there's a philosophy, a beautiful philosophy behind this, because we have to revisit the relationship between thermodynamics and kinetics. Knowing this, we know that it's not possible to describe how is going to be the temporal evolution, the change, the rates of a chemical reaction based only on the equilibrium composition of this chemical reaction. In other terms, mathematically speaking, we can say that kinetics coincides with the thermodynamics at the limit of time infinity. But now with this equation, notice that a thermodynamic parameter such as the equilibrium constant relates concentration profiles that occur far from equilibrium, that occur right from the beginning of the chemical reactions. And the relationship between these concentration profiles is given by a thermodynamic parameter such as the equilibrium constant. And for instance, if I know one concentration profile, I can know the other, knowing also the equilibrium composition. This is the equilibrium constant. This type of invariants, the theoretical background for this type of invariants is given in this paper, and also there is some experimental confirmation. This is a more recent experimental confirmation, in this time for a nonlinear chemical reaction. And there is another one, another experimental confirmation using an electrochemical cell in this time. So let's make it more complex by adding a reaction. Let's consider now that two-step A goes to B goes to C. We know the element conservation holds, A plus B plus C remains constant. There is a stoichiometric relationship here. And also this type of invariants can be calculated for more complex linear mechanisms, okay? BA over AB, disregarding that the reaction B goes to C occurs. It can be also calculated from C and B, and also from A and C, and this time we have a composite equilibrium constant. But now we found for this step, for this chemical mechanism, for this mechanism, a new type of invariant from scale incremental conversion. Scale incremental conversion is defined as follows here. It's some kind of a normalization. It's a concentration profile normalized to its initial concentration, divided by the difference between the equilibrium concentration and the initial concentration. We found out that ratios of differences of this type of terms, of scale incremental conversion terms, are constant, okay? We have here 4 arguments to fill in this equation, okay? So we may have many combinations of scale incremental conversion terms. Also, every scale incremental conversion term is related to an initial condition. So in the paper there, we found many invariants, and I will highlight some of them to you. We have thermodynamic invariants, of course, functions of the equilibrium constants. These are the 4 arguments that we have to put here in this expression to obtain the invariant. This is another sum of the table of invariants, and I would like to call your attention that appears a kappa here defined as k plus 1 divided by k2 minus. This is a non-thermodynamic ratio of kinetic coefficients. K1 plus and divided by K1 minus is the equilibrium constant of the free reaction. This is a thermodynamic ratio of kinetic coefficients, but this one is not. And here we have expressions that mix equilibrium constants with this non-thermodynamic ratio here called kappa. So for this chemical reaction here, we know all these type of invariant expressions, and we were able to find another one from conservatively perturbed equilibrium. This is a nice feature. What we're going to do here, for instance, is we will choose an unperturbed substance, in this case A, for instance, and we will make a second experiment choosing the initial concentration of A as equal to the equilibrium concentration of A. And the equilibrium and the initial concentrations of B and C will be their equilibrium concentrations affected by a delta value. Okay, so you can see that the total mass balance remains the same in the second experiment. But the behavior of the unperturbed substance, in this case A, will start from equilibrium and will go back again to equilibrium. So it'll go through an extreme value. Here I'm showing you some plots for this mechanism. Here A is an unperturbed substance. You can see that it starts from the same value and ends in the same value. So it goes through an extreme value. And we found out that if I put this plot to 0, subtracting the equilibrium concentration, the ratios of these normalized concentration profiles yield also invariant expressions. These are typical plots, A, B, and C. Here the subscripts indicate that the substances that are not perturbed, they are not unperturbed. The ratio of these three concentration profiles, after putting them to 0 by subtraction to the equilibrium constant, the ratios yield invariant expressions. Function of, as in this case, these are the equations. Function of the equilibrium coefficients, for short, function of the delta values of the first experiment and the second experiment. This is the perturbations on the two experiments. And here you can see that appear another, in this case, this one, another non-thermodynamic ratio of kinetic coefficients, okay? Here we substitute the sum of the delta values in the expression. These are the invariant expressions substituting the delta values in the first equation, in this case, the concentration profile of A divided by the concentration profile of B corrected to their corresponding equilibrium concentrations. And for the second equation, we obtain these invariants here. Here we have kappa in and kappa out. These are both non-thermodynamic ratios of kinetic coefficients. And luckily, this procedure, these equations here, these two equations here, we're able, or is it possible to extend these two equations to more complex linear mechanisms, not only two-step mechanisms, but actually these two equations here are particular cases when applied for more complex linear mechanisms, as will follow now. The first expansion that we did for complex mechanisms, it's shown in this paper, and it arises. I will show you back the equations. This is the polar two steps of mechanisms. Arises because if you are able to find in a more complex linear mechanism a two-step submechanism. For instance, in mechanism 3, the mechanism DCE is a two-step submechanism within this mechanism here. And for instance, and we have more here are listed. This mechanism here does not have a two-step submechanism. But if we're able to find a complex linear mechanism with two-step submechanisms within them, these equations here are valid too. Disregarding the parallel equations that happen elsewhere. And the other extension, if you notice the second equation that involves A and C, the poles of the two-step mechanism separated by the substance B. Actually, the substance B can be not only a substance, but a whole submechanism. This means that I can apply the second equation here. This second invariant expression can be applied to any complex linear mechanism, because considering only the poles, for instance, this is the paper where we published this. For instance, the mechanism number one is the second, the two-step mechanism here is the same. But if we have a three-step mechanism, we can find an invariant with A1 and A4, okay? And here will appear a composite equilibrium constant here, A1 and A5 in this case. There is an invariant relating them. And here we have composite equilibrium constants. It is possible then to extend the second equation here to any complex linear mechanism, considering the poles of the linear mechanisms here, as in this table is shown. Luckily, or voila, if you want to know more, we wrote last year a review with all these invariants and some more in this paper. So as some sort of conclusion, we obtain thermodynamic and non-thermodynamic invariants from special functions that relate concentration profiles. Thermodynamic invariants are related to thermodynamic ratios of kinetic coefficients, and non-thermodynamic invariants also appear, which is from non-thermodynamic ratios of concentration of kinetic coefficients. In order to obtain our invariants, we needed at least 2 experiments with reciprocal initial conditions. And we were able to apply, to obtain invariant expressions for any complex linear reaction. Thank you very much, and I'm open for your questions.
Yeah, thank you, Mr. Branco. I think there are some questions from the audience, so please go ahead.
Elena.
Okay. I have a question. Should I consider only linear mechanism, or I can consider non-linear mechanism? I mean, if I have a system which have 2 stable states, how I can found invariance in this case?
This is not easy to answer. We will have to analyze the mechanism and check if it's possible. And you have to solve the mechanism and find mathematical relationship. If it's linear, it could be possible to do it. And we have some results for nonlinear reaction. But yeah, the mathematics gets very complicated, even for simple nonlinear reactions. But this is a case-by-case answer. I cannot, we can't answer if a certain nonlinear mechanism will have or not an invariant expressions to be calculated.
Thank you.
You're welcome.
Okay, then I've got a question. So on your conclusions slide, you wrote that at least 2 experiments are needed.
Yes.
So how does the number of experiments depend on your system for that?
The number of experiments is based on the different initial conditions that you can apply. If you can make experiments, or at least 2, with different initial conditions, okay, this is the number of the experiments that we need. It's not repeated experiment with the same initial condition, like maybe to make some improvement in the statistics, in the confidence of your parameters. It's a totally different experiment, but from other initial conditions. And of course, this is defined by the mechanism itself.
Okay, thank you. Any more questions? Okay, I don't see another. So thank you once again, Mr. Branco, for your nice presentation. And we move on to our next speaker. This is Dr. Stanislav Žižek from Institute of Solid State Chemistry and Mechanochemistry of the Siberian branch of Russian Academy of Sciences, Novosibirsk, in Russia. So thank you, and the stage is yours.
Okay, thank you for presentation, and I hope you can hear me. And now I will switch to the my presentation. I should start the demonstration of the screen. Okay. Okay, now I believe that you can.
Yeah,
you can see
perfectly.
Okay, thank you. Let's start. So I will start right from the second slide. So our study is related to the reaction between.
I'm sorry, Stanislav. Could you please switch camera on, because we are streaming to YouTube and we stream all the presenters. Thank you.
I'm sorry.
It's all right. Just switch camera on.
So, okay.
Now
it's switching. So our study is related to the reaction between oxygen and the non-stoichiometric oxides, such as perovskite-like oxides AbO3, like this. And it has long been known that such oxides are able to stably exist in a wide range of oxygen stoichiometry 3- delta. And at the same time, they have high ionic oxygen conductivity and also high electronic conductivity. They are mixed ionic electronic conductors. These properties can make it possible to use materials from such oxides in various devices, in the chemical industry and for the power production. However, the number of unresolved problems is still large, both engineering and fundamental. One of the fundamental problems is an incomplete understanding of the mechanism of the processes in this reaction and their correlation with the composition and structure of oxides, and as a consequence, weak possibilities for controlling the characteristics of oxides and materials. As you can see, this reaction under consideration can be considered in two ways: as an ordinary reaction between two substances like this, and also as a catalytic reaction in which the oxide as a catalyst participates in the transformation between different states of oxygen, molecular oxygen in the gas and reduced oxygen in the lattice. So this slide shows you the presentation of this reaction as catalyst, a catalytic reaction. In this version, the reaction begins with the chemisorption of oxygen molecule on the surface of oxide catalyst. It continues through a series of stages in which various intermediates are formed and transformed to each other. So molecule dissociates. It can dissociate on the initial side of chemisorption, or it can dissociate at a surface defect, at various surface defects. Then chemisorbed molecules and surface vacancies migrate toward each other and acts of charge transfer take place. The reaction chain ends with the incorporation of oxygen ions and their diffusion into the bulk of the crystal. The principal problem in studies of the reaction is to elucidate the main reaction route, the main set of intermediates, and the limiting stage of the chain of surface transformation. Modern computational methods show that the main contenders for the limiting stage, the rate-determinant stages, can be the stages of migration of surface vacancies to the chemisorbed atoms or molecules, or dissociation of the molecules in place without the participation of defects. If we talk about the possibility of experimentally testing this hypothesis on the basis of kinetic data, then it is very likely that we can only distinguish between stages with a different stoichiometric coefficient lambda, the number of acts at the limiting stage required to transfer one molecule along the reaction chain. It can take two values, one for molecule and two for oxygen atom. In this scheme, it is important that oxide is a parameterized catalyst. Its properties depend on the current stoichiometry. This means that the Bronsted-Evans-Polanyi relation should be fulfilled for the reaction. So, the methods for studying the reaction. There are two main methods for studying this reaction used. The first is relaxation on the left. The equilibration of the oxide and oxygen system started with a sharp deviation from equilibrium, and the second on right, is stationary permeability of membrane. That is the measurement of oxygen flux through the oxide membrane at a given chemical potential gradient. Traditionally, relaxation is considered as a method of fundamental research, providing information about the effective constant of the surface exchange rate and the diffusion coefficient, and permeability as a kind of applied study which characterizes the oxide as an oxygen conducting material. However, it is clear that in both cases, the process is composed of the same chemical steps, and the result of these two methods must be consistent. However, the results of a permeability experiment are not always analyzed to obtain the same constant as in the relaxation method. Moreover, various empirical models of kinetics are used often, so the resultant constants are difficult to compare with each other, except perhaps the diffusion coefficient. This is the main reason why only a small number of publications can be found comparing the results of the permeability and relaxation. In fact, we only know a single paper which shows the coincidence of the diffusion coefficients and their activation energies. In other four articles, various contradictions are observed between the results, both in constants up to 2 orders of magnitude and in activation energies up to 2 times. And we do not know of a single article where the values of the rate constants of the surface reaction were compared. Therefore, we have chosen to compare the rates of the surface reaction as the main aim of the study. For this, it is necessary to use thin membranes, hollow fiber membranes, like this, in which oxygen permeation is controlled by the rate of the surface reaction. So, to be able to compare the experimental results in these two methods, it is necessary to use the same kinetic model of the surface reaction. Traditionally, the relaxation methods use a model of a first-order reaction with a constant reaction rate constant, so the deviation from the equilibrium and the resulting driving forces are assumed to be small, like this, and a constant key chemical. However, the conditions are actually used even in a relaxation experiment do not fully satisfy this requirement. And especially the conditions is not satisfied in permeability experiments. Then it would be more correct to use the approach of non-linear, non-equilibrium thermodynamics in the second part of the slide. In this approach, the overall reaction rate is equal to the rate of the slowest stage, the rate determinant stage, while the rest of the stages are in equilibrium, in thermodynamic equilibrium. There are fast stages, while the driving force of the rate determinant stage should be, it is uniquely determined through the total driving force, and the stoichiometric coefficient lambda. As for the potential of the transition state, since the properties of the oxide should depend on the stoichiometry, the transition state energy should depend on the standard chemical potential of the limiting stage. This can be determined by a well-known linear relationship in which the beta coefficient characterizes the symmetry of the activation barrier of the rate determinant stage. And it is also known as the Bronsted coefficient. This consideration leads to the expression shown here for the reaction rate. This in the upper part, the equation for the reaction rate. And if we consider the case of the low driving force limit, it is reduced to the traditional equation of the first order reaction. So it is important that these constants R0 and key chemical turn out to be proportional to the power function of the equilibrium oxygen pressure, which is always observed. This part of the equation, or this part, and this dependence always observed in standard experiment, relaxation experiments. And we see that the exponent n is defined only by the relation between coefficients beta and lambda. So this is the standard scheme of the relaxation experiments, when the sample lies in the reaction line, and it is based on the methodology developed by us for measuring the relaxation by the relaxation of partial pressure of oxygen. The sample is equilibrating with the gas flow at the initial oxygen pressure, and then the pressure switches, and the installation records the kinetic of the gas composition at the outlet of the reaction according to the signal from the oxygen sensor. So, for a correct description of the transformation kinetics in oxide particles, it is of course necessary to take into account the microkinetic of the reaction between solid and gas phases. So we used equations developed in the framework of known TIS hypothesis, the tanks in series hypothesis. So the second setup is for the permeation. The experiment of the permeability of membranes is carried out in an installation which uses scheme of counterflow of gases with high oxygen content outside the membrane and low content of oxide inside the membrane of content of oxygen. Sorry. To heat the membrane, original technique is used. The membrane is heated by electric current. So for this experiment, similar to the previous macrokinetic model, is also used. So I will not stop on this slide lengthy. So these are views of the samples for this is a hollow fiber membranes, and this then samples for the relaxation experiments. So we selected a composition of barium, strontium, cobaltite ferrite with the small addition of molybdenum. It is based on the well-known BSCF oxide, which have record oxygen conductivity, and this modification makes this conductivity is even higher. So this is thermodynamic equilibrium diagrams obtained by the method of quasi-equilibrium relaxation, and here we see the signs of the phase transition between two phases P1 and P2, which both of these phases are cubic. They have cubic symmetry, and the exact nature of this transition is still unknown, but it is takes place at average oxidation state of B ions as B3+. So here we see the areas regions of pressures, oxygen pressure used in different experiments. This is for the relaxation experiment, and this high pressure part of the permeation experiment, and this pressure is the result of the permeation. And we see interesting possibility to study the influence of the phase transition, because some part of the relaxation experiments are taken in the region of the T2 phase. So this is the example of the relaxation kinetics. 200 kinetic curves were acquired, and we analyzed them to obtain the dependency of constants. So this constants depends as power law on the per oxygen pressure, with power exponent number about 0.7 for the surface reaction rate, and about 0.5 for the diffusivity. And these values obtained are close for that known for the BSCF in different papers. So the interesting part is that we do see the influence of the phase transition, in which the exponent n is twice lower than in P1 phase, exactly 0.3. And this should mean that lambda switches from 1 to 2 at the phase transition. So we can speculate that the phase transition causes the change in the rate determinant step from the simple dissociation or migration of a molecule to the surface defect to the situation when RDS is migration of surface chemisorbed oxygen atoms to the defects, or defects migrate oxygen vacancy, surface vacancy migrate to the oxygen atoms. So about the temperature dependence for the diffusivity and the reaction rate, we obtained following activation energy, and activation energy known from other papers are larger, and this is a common situation in this type of experiments, in which very large deviation between the activation energy often observed in different experiments made by different authors. So the results of the permeation experiments are simple. They are on the single slide. This dependence of the output oxygen pressure in the output gas flow from the high oxygen pressure outside the membrane. And these experimental points, were modeled with above described model to give exponent the same power law dependence of the rate, with the exponent about 0.6, which is close to 0.7 from the relaxation experiment. So this is the main result of our work. And we see, if we compare the final result of this work, we see that the value of the equilibrium exchange rate, the R0, almost equal in these two experiments. They have almost equal activation energy, and they differ only by 2.4 times from each other. The permeation is lower. And this difference can be even explained if we see at the exact structure of the membrane, and we see that there's not only one dense layer, but there are external, maybe two layers which can be dense too, which gas dense too, and then we can estimate that the rate of the reaction should be reduced by a factor about 3. Thus, we obtain.
Please conclude your talk.
Okay, this is conclusion, right for you.
Right.
So we have 4 conclusions. There are some details, but 2 main conclusions. There are 2 main conclusions. First, of course, we obtained the main answer to our problem. First said problem that the results of these 2 experiments coincides each other. This is the first main conclusion. The second conclusion, we have some suggestion about the mechanism of the RDS for the phases P1 and P2. Thank you for your attention. That's all.
Yeah, thank you very much, Mr. Žižek. Yeah, during the limited time, I suggest that we gonna put the discussion into the coffee break after the next speaker.
Okay, thank you.
After next talk, so I think you can address all questions to Mr. Žižek directly in the coffee break. So thank you. And let's move on to our last speaker. This is Professor Marina Slin'ko from Semenov Institute of Chemical Physics of the Russian Academy of Science in Moscow, Russia. The floor is yours.
Professor Slin'ko, could you please switch your camera on? Включите, пожалуйста, камеру и микрофон. We cannot hear you.
Can you hear me now?
Yes, and yes. Please switch your camera on. Вы камеру включите.
Камеру включите. Она у меня включена?
Нет, она у вас выключена.
This is my first experience to demonstrate. So, just now. So, on behalf of my colleagues, I would like to tell you about the new type of spatiotemporal patterns which can be observed during the oxidation on nickel at atmospheric pressure. Up to now, there are 2 types of special structures which can be observed on the catalyst surface. The first type is either thermal surface waves, and just now you can see the experimental results from the Nobel Prize lecture of Professor Ertel, where he demonstrated spiral waves during the oxidation of a platinum-110 single crystal surface. So the dark color corresponds to the surface covered by oxygen, and the bright color corresponds to the surface covered by carbon monoxide. At atmospheric pressure, until recently, only non-isothermal surface patterns have been observed. And here you see the example of the so-called hotspot pattern, which has been observed during the oxidation on palladium-supported glass fiber catalyst. You can see that the amplitude of temperature oscillations can be as high as 200 degrees. Oscillations during the oxidation on nickel have been discovered only recently, only 3 years ago. And they differ from oscillations during the oxidation on platinum, palladium, and rhodium catalysts in that they observed not an excess of oxygen, but an excess of carbon monoxide. And they are kinetic oscillation because, can you see, the temperature oscillation is not large. And the feature of oscillation is that with the temperature increase, the period of oscillations at first decreases as usual. But finally, at 580 degrees, the period of oscillation decreases and oscillations becomes irregular. So the special construction of the reactor and the furnace allowed us to follow the color of the surface catalyst. And it was demonstrated that during oscillation, the color of the catalyst changed from the light, bright, corresponding to the reduced nickel, to the dark, corresponding to the oxide state. And the process of reduction leads to the increase of reaction rate, and oxidation causes the decrease of activity of the catalyst. The next slide will demonstrate you the recording of this experiment with photo-video camera, and you can see very quick reduction and then slow propagation of the wave of oxidation, which moves in the direction of the reaction of the flow of the reactant in the reactor. The observed color of the nickel foil depends on the interference between the light reflected from the bottom of the oxide film and that reflected from the top. That is why you can see black and also first order colors. So black transforms to straw, brown, and then blue. In some experiments, the second order colors also could be noticed. It must be noted that the video speed increased 4 times compared to the reality. So here you see the propagation of the front of oxidation and the change of colors due to the increase of the thickness of nickel film. This is the picture corresponding to the regular oscillations. But as I told you, at 580 degrees of Celsius, the character of oscillation changed. First of all, you will see on this video that the wave of propagation of the oxide field decreases, and at some time, the forward motion of nickel oxidation stopped, and the sharp boundary between the oxidized and reduced state remained unchanged for some time, and accordingly, the step in the reaction rate appears. And this is the reason of the increase of period of oscillations at this temperature. And if this pulse occurs randomly, so we observe irregular oscillations. In order to, if you have instantaneously very quick phase transition on the catalyst surface and no gradients in the gas phase, you can use for modeling of oscillations by the point model. But if to model wave phenomena, we need the distributed model. And the point model was based on the well-known Langmuir-Hinshelwood mechanism, which was added by steps of surface oxide formation and surface oxide decomposition. Here you see the parameters for the modeling found from the literature. But it is well known that this mechanism reminds the well-known Sale-Turner-Maple mechanism, which was created for simulating oscillations during the oxidation on platinum, palladium, and rhodium catalysts. However, it is known that this model and mechanism does not produce oscillation in oxygen, in carbon monoxide excess. They can produce oscillation only in oxygen excess. That is why mathematical model was modified, and we consider the peculiarities of CO adsorption of a nickel catalyst. It was demonstrated that CO adsorption of a nickel catalyst follows the precursor mechanism when CO molecules can seek out active sites, which may be in a very low concentration on the surface. And the rate of CO adsorption was calculated according to the Kisluk relationship. So we also considered 3 forms of oxygen on nickel. This is adsorbed oxygen, which can transform to the surface oxide, and it also can penetrate into the subsurface layers and namely subsurface oxygen, will define the color of the catalyst in mathematical modeling. So the point mathematical model includes equations which describing the variation of oxygen and carbon monoxide on the catalyst surface, the variation of the surface oxide, and this is the block of equation which describe variation of surface coverages. Next equation describe the variation of the subsurface oxygen, the equations describing variation of gas phase concentration, and finally equation for the dynamic of catalyst temperature. And the next slide will demonstrate you the results obtained with the point model. You see that the very small oscillation of surface oxide can lead to the large concentration of the subsurface oxide. And if the concentration of the subsurface oxygen is large, it corresponds to the dark color. And you see that very small amount of free sites exist at this moment, which corresponds to the minimum of the reaction rate. And when concentration of the subsurface oxygen is small, this corresponds to the light color. And you see that there is maximum of free active sites, which corresponds to the maximum of the reaction rate, which corresponding to experimental data. And to simulate the wave phenomena, the distributed model was based on the following system of 3D convection diffusion reaction equations, where CK concentration of the gas phase oxygen, CO and CO2 concentration, or the gas velocity, decay diffusion coefficients. And these partial differential equations are coupled with a space distributed kinetic model, which gives the source terms at catalyst surface. And the method of lines, a definite volume method, were used to transfer partial differential equation into ordinary differential equations. So the reactor volume was divided into NR equal control volumes with this space step, and for each control volume, the effective diffusion coefficients were calculated using the relation of Foulier-Schatte-Giddings and the Wilke equation. And so the total number of equations is equal 4/10 in 5 degrees. So the next slide will demonstrate you the results which are obtained with a distributed mathematical model. And when I switch on the video, you will see the gradients of oxygen along the reactor, gradient of CO2 along the reactor. So you will see the view on the catalyst top view, also the variation of subsurface oxygen, free active sites, and CO2 out the reactor, and the view of the catalyst. So we begin with the black catalyst, which is oxidized. And here you see that with the time, reaction rate increases, the concentration of bulk oxygen decreases, the number of active sites increases, and at some moment, the quick reduction is occur. You see that the wave appears as an experiment at the entrance of the reactant mixture. And then again, the catalyst is oxidized, you see. The large concentration of subsurface oxygen, which is decreasing, the free active sites increasing. Just now again, reduction occurs, and you see the large gradients of oxygen and CO2 pressure along the reactor. And due to this gradient, the wave of reduction, the wave of oxidation appear. So the conclusion of this work is, first of all, we demonstrated that kinetic special structures can be observed not only under ultra-high vacuum conditions, but also under normal pressure conditions. So we also demonstrated that the kinetic waves under normal pressure conditions are oxidation reduction processes of the catalyst. And we can compare kinetic waves under ultra-high vacuum condition and under normal pressure conditions. And we can understand that while under ultra-high vacuum conditions, the rate of kinetic wave propagation always constant, and the spread rate of propagation always increases with the temperature increase. The rate of kinetic wave propagation under normal pressure condition is not constant and can decrease with the temperature increase. And finally, we demonstrated that kinetic waves under normal pressure conditions arise due to the oxygen gradient in the reactor volume as the result of mass transfer limitations. So thank you very much for your attention. I'm ready to answer questions.
Yeah, thank you very much, Professor Slin'ko, for this nice talk. And I think we have enough time for a couple of questions. And I see one from the audience. So Elena,
yes, thank you. Nice to meet you, Maria Mikhailovna.
Also, greetings to you.
I have a question about irregular oscillations. As I understand, you say that the reason of this non-regularity is some kind of pulse. And what is it? What would you say about this phenomena?
Yes. So is it seen here?
Yes.
Yes. So the pulse happens when the concentration of oxygen in the reactor is not enough for wave to spreading through the whole surface. And this happens at high temperature where more layers of nickel participate in the process of oxidation, and reaction rate is high and concentration of oxygen decreases.
Thank you.
Mm-hmm. I've got a question concerning this slide. How thick is this reactor? So what is the distance of the radial distance of this reactor type?
So the diameter of the reactor was 6 millimeters, and so it was, and there inside it was the nickel foil, and so the gradient of concentration appeared. It was not the continuous steam tank reactor.
Mm-hmm, mm-hmm. So do you think that the boundary of this nickel foil has a certain effect on the oscillatory nature of this foil?
Certainly, because so the wave form of oscillation completely depends by the properties of the wave propagation. If it is stops, and so so you see this is the highest reaction rate when all the surface is reduced. Then when oxidation began to decreases, and it stops for time at that level when the square of reduced surface is constant.
Mm-hmm, mm-hmm. Yeah, very interesting. And you did these experiments on a foil. What do you expect if you use a catalyst with a certain thickness? So that means reaction diffusion inside this porous catalyst comes into play. Do you expect similar behavior or very different ones?
And so we did not use the porous material, but but I hope that we shall do this. It must be tested experimentally.
Mm-hmm, mm-hmm. Yeah, I can imagine that then a little bit different scenarios appear, but yeah, very, very interesting.
Maybe.
That. Okay.
Can I have a question?
Sure.
Maria Mikhailovna, very happy to see you. I have a question about the very interesting results of modeling using the distributed model. So as I noticed, you in the point model you consider you account for temperature changes, but here for distributed model, do you account for temperature changes, or you consider the temperature as a constant? Because I don't see the picture for temperature in the results modeling.
We calculated the temperature also, but the temperature is not crucial in this. So the same results will be obtained as without not considering the variation of temperature, because the variation of temperature during oscillation is small, and it is not a crucial parameter in the model.
Mm-hmm. Okay, and the second question is that you observe very interesting experimental results. You observed the concentration waves going concurrently with the movement of the gas flow. Can you imagine, is it possible that there may be some concentration waves that under some definite conditions may go upward, so in countercurrent direction to the gas flow?
If the wave of oxidation is going in the flow of the direction, so the wave of reduction, you may notice, it is going in the opposite direction. So the mainly gradients of concentration determine the initiation and distribution of the waves.
Okay, very interesting. Thank you very much.
Thank you very much also for your questions.
All right, if there are no more questions, and I don't see anything from the audience, thank you very much once again for this nice talk. This was our final speaker for this first session. And now it's time for coffee break until 11 o'clock. And then we have the second session here in Hall 1. Thank you very much.
Thank you.
And see you later. Bye-bye.
Thank you very much. Yeah, thank you.
Thank you. We continue the section 1, Advances in Chemical Reactor Fundamentals, and the first speaker is Professor Elena Lashina, Boreskov Institute of Catalysis of the Siberian branch of Russian Academy of Science, Novosibirsk, Russia. Please, Elena.
Thank you for presentation. And my report devoted to the study of non-stationary dynamics of oxidation, and these studies was dependent on the structure of palladium-CERIA catalysts. And I will present the result of experimental and studies and the result of mathematical modeling. CERIA is often applied in catalytic studies because of its structure and reduced properties. In reduced conditions, for example, in reaction with CO, CERIA surface reduces and the bulk of CERIA also can reduce too, because of the oxygen diffusion from the bulk to its surface. And the CERIA catalyst demonstrates the activity at high temperatures. When we add to CERIA palladium, then under different conditions of the catalyst preparation, we can obtain different structures of palladium on the catalyst. For example, such as solid solutions, clusters, or palladium oxide nanoparticles. And depending on the palladium structure, the catalyst demonstrate the activity at different temperatures. In this slide, I present the result of the temperature program reaction of the CERIA palladium catalyst with CO. In this case, CO from the gas phase react with the catalyst, and the catalyst reduces. We have no oxygen in the gas phase. Oxygen only in the structure of the catalyst. So we see the CO2 evolution, and in this figure you can see the different curves which are dependent of CO2 evolution on the temperature for the different catalysts which will calcinate at different temperatures. Starting from 450 Celsius degrees till the 1000 Celsius degrees. And in this curves, we see three peaks. And the first peak is a low temperature peak, and we corresponded to the reduction of the palladium oxide clusters. The second peak is observed due to the reduction of palladium oxide nanoparticles. And the third broad peak concerned to the palladium solid solution. To describe this experimental data, we also take into account the result of another experimental studies, such as electron microscopy. And in this slide, you can see that for the catalyst which will calcinate at 600 degrees, in this picture, green color correspond to this CERIA active center, and red color correspond to the palladium active center. And for the catalysts calcinate at 600 degrees, the palladium is in state of solid solution or small clusters. And when we increase the temperature of calcination to 800 degrees, we observe the larger palladium clusters and palladium oxide nanoparticles. So we want to describe this data, experimental data, using the method of mathematical modeling. To do this, we consider the mechanism of the oxidation over CERIA. To develop the mechanism, we consider this scheme. In here, I present that the bulk of CERIA we presented as layer by layer scheme, and the reduction of the CERIA bulk can proceed due to the oxygen transfer from the bulk to the surface. And the constant of oxygen diffusion from one layer to another can change from layer to layer. We consider the following kinetic scheme, which describe the concentration of oxygen over CERIA, over the surface of CERIA, and in the layers of the CERIA bulk. Also, we consider their changes in time of volume percent of CO and CO2. To describe the experimental data, we estimated the initial concentration of oxygen over the surface of CERIA and in the bulk of CERIA, and the constant of reaction. This slide demonstrates the result of simulations. in this figure, dashed blue curve is experimental data, and red curve is result of simulations. In accordance with the simulations, the experimental data could be good described when we consider the transfer of oxygen from 3 subsurface layers. And in this case, we see that CO2 concentration is very low, and in this case we consider that the concentration of oxygen which take part in the reaction also low. Then we consider the system, Palladium-CERIA system and palladium catalysts, which were calcined at 450 degrees and 600 degrees. These catalysts have palladium as solid solution and palladium oxide clusters over the surface of catalyst. And to describe the activity of this catalyst, we consider these 5 steps S4 from S4 to S8 of reduction of these palladium centers. And so we add to the previous kinetic model more equations and describe the experimental result for this catalyst. And in this figure, we see that at low temperatures, active palladium oxide clusters are active. And at high temperatures, the broad shoulder correspond to the reduce of CERIA oxide bulk. And when we increase the calcination, temperature of calcination, the palladium changes the structure, and we observe palladium oxide nanoparticles. So we need to consider them too. And we described using the simulations so that we consider that palladium oxide clusters are more active at low temperatures, and according to the result of the simulations, we need to consider more layers in the CERIA bulk to qualitatively describe the broader peak at 300 Celsius degrees. And in this case, we see small peak, which corresponds in this curve at 1000, which correspond to the palladium oxide nanoparticles. Then we increase the temperature of calcination till 900 degrees, and in this case, the palladium, all palladium over surface was in the as palladium nanoparticles, palladium oxide nanoparticles, and to describe the reaction of this catalyst, we consider the additional step which describe the reduction of palladium, of the volume of palladium oxide nanoparticles. And this slide demonstrates the results of the simulations, and once again, the blue dashed curve is experimental data. And we see that the peak at low temperature at 200 degrees is sharp, and it corresponds to reduction of palladium oxide nanoparticles, while the broad high temperature peaks correspond to reduction of CERIA oxide surface and ceria oxide bulk. And because of the decreasing of the catalyst surface, we need to consider more layers in palladium, more layers in ceria bulk to describe the experimental data. And thus the structure of palladium-CERIA catalyst depends significantly on conditions of the ceria preparation. And depending on the state of palladium, the catalyst active at different temperatures. Using the methods of mathematical modeling, we have confirmed the experimental TPR-CO data on the oxygen flow from the ceria bulk. Increasing of temperature of calcination caused the subsequent formation of palladium oxide clusters and palladium oxide nanoparticles from palladium solid solution. Moreover, the reducibility of the ceria oxide surface and the bulk also increases under increasing of the temperature of calcination.
In one minute more.
Okay, and thank you, and thank you for your attention. And I think we all, as these kids who are interested in what they see and wanting to know what is it.
Okay. Thank you very much for your presentation. And who have questions, please, the audience? So if there are no questions, I would like to ask you. So you have a very mathematical model which contains many equations and many steps there are. And you told that there are diffusion coefficients differ from one layer to another. Can you tell me, where did you get the parameters for so many stages and first and moreover for different coefficients for each layer?
And we consider these models as from one to another. And we estimated, first of all, some parameters for the ceria. And what? Okay, some parameters for the ceria catalyst. This in these estimations we used. This estimation we used to describe the changes of CO2 which observed for the palladium-CERIA catalyst. These parameters we estimated all of these parameters. This rate constant we estimate.
So how many fitting parameters contain your model? How many fitting parameters?
For ceria, we have 9 parameters to fitting.
9 parameters.
Yes.
And what about diffusion coefficients for each layer?
Diffusion coefficients decreases from layer to layer. This means that the more number of layers you consider, the lower the diffusion coefficient.
Okay, so are there more questions? Okay, so if there are no questions, let's go to another presentation. And the next speaker will be PhD student Nafal Al-Hamdi from University of Science and Technology, Saudi Arabia. So please.
All right, let me just share my screen.
Yes, you are, okay.
Looks good?
Yes, it's good. We can see.
All right. Excellent. Thank you very much. Good morning and Good afternoon, good evening to each one of you. My name is Nawaf Al-Ghamdi, and I'm a PhD student at the Clean Combustion Research Center at KAUST, King Abdullah University of Science and Technology. And I work with Professor Mani Sarathi here at KAUST. And it's really a pleasure to be here with you today and to talk about a microkinetic description of carbon monoxide oxidation over rhodium. And this is a work in progress. And so I'll share with you the plan, the problem we're trying to identify and work on, the experimental data we have, and the plan forward. So the outline is to talk about CO oxidation first and the relevant to after treatment applications. We'll go through the literature review with a focus on the microkinetic models, and then what our objectives are to fill in some of the gaps that are in the literature in these models, and then the methodology and preliminary data, the experimental setup we're using, the results we got, and our modeling approach. And then the plan forward, which is where I'd be happy to receive suggestions and recommendations, and then a summary at the end. So let's first start by talking about passenger cars and the high energy consumptions they have. This is a diagram that shows you the energy consumption in 2017. And this inner circle here shows the total consumption. So if you look at transport, for example, obviously it's a big thing that takes about 35% of our energy needs. But if you look at passenger cars, they alone take up 21% of the global energy demand. And so the idea here is that this is part of the energy landscape that takes up a lot of energy, and it has associated emissions, and it would be very much worth it to still try and elevate the level of after treatment we have. And so in passenger cars, we'll have gasoline and diesel as the dominant fuels, and this is the main point in this slide. It's true that by 2040, the EIA, the Energy Information Administration, is expecting a decrease in the gasoline shares from 39% to 33%. Diesel is also expected to go down from 36 to 33, but they will still be the dominant fuels by 2040. And if you look a little bit on the graph here on the right-hand side, the idea is that you'll have things like electrification coming into the picture. You'll have natural gas being used, liquefied and then used as fuel as well. But we're still talking about gasoline and diesel as dominant fuels. And so if we look into passenger cars and the emissions that we have from them, there's CO, there is unburned hydrocarbons, there is NO, there's soot, sometimes you have SO2 if we're talking about diesel or marine applications. And what we try to focus on in this work is CO. And the way CO is dealt with in after treatment emissions is that it's oxidized. So we can go from CO to CO2. And this is what the three-way catalyst in your gasoline cars does, for example. The temperature range of interest for after treatment is somewhere between 100 to 300 degrees Celsius. We're talking about near ambient pressure. It's not exactly ambient, but it's also not much higher than that. And we expect water to play a role. And we'll talk about this a little bit in the slides after this. And water is present in the after treatment or in the exhaust emissions as we have complete combustion to CO2 and H2O. And so taking that into account is also important. Let's look into what's available in the literature. I'm not going to be able to review everything in the literature, but at least some of the kinetic studies that are out there and what we see typically. So you'll have a mechanism that typically shows something like this. You have adsorption-desorption reactions where O2 desorbs dissociatively on the surface. So O2 plus 2 sites will give you 2 single oxygen atoms. CO adsorbs as well, and CO2, so you allow the desorption and adsorption-desorption directions. And then you'll have some surface reactions. Most of the mechanisms will show this bottom reaction, where you have CO reacting with a single oxygen atom, so provides CO2, and then that goes to the gas phase. But some mechanisms will also show CO decomposing on the surface to carbon and to oxygen. And typically, if you see coking, you'll include this reaction. If not, then you skip this one and include the last one. But this is still a reaction that is very much under study. And if you look in 2020, for example, there was a new surface science discovery where they added the reaction here. This is a paper by Shimokuri et al. In 2020, published in Combustion Science and Technology. And the addition they found through characterization techniques is that you have this sort of twin adsorption on the rhodium surface. So you have 2 CO atoms adsorbed on one rhodium surface, reacting with one oxygen, providing CO2. CO is still adsorbed, and then you're left with one rhodium site. So this is typically what we see in the literature. Then let's look about previous models that were published. And I put in parentheses here some, because it would be virtually impossible to go through every model, but at least I provided one highly cited model here on the left side by Professor Matteo Maestri, and this is back in 2008. And so here on the left-hand side, we see a model for methane chemistry on rhodium. They took a multi-scale hierarchical approach, and it is thermodynamically consistent, which we don't see a lot in the literature. Actually, we see a lot of inconsistency from a thermodynamic perspective. This relies on the semi-empirical UBI QEP method, and this is a method where you start with adsorptions of single atoms, and then you go up to activation energies and the necessary parameters for the Arrhenius equation. And this was an improvement to a previous model published by Professor Dion Vlachos at the University of Delaware just a few years before. Another model I'd like to highlight here also is the Cardenas et al. Model. This is from Professor Duchman's group in Germany. They also took a multi-scale hierarchical approach. It is thermodynamically consistent, and I'm highlighting it here because the experimental data were obtained from a reactor that is interesting to us, and it is the one that we used in the experimental data. So these are two that I'm highlighting, and the thing I would like to point out here is that both models do not predict the low temperature reactivity that we observed in the lab, and I will show this in just 2 slides after. So then, knowing all this, what are our objectives? Our objectives were to investigate CO oxidation at low temperature for after treatment applications. The idea is to do this in the absence and presence of H2O. And the point behind including H2O is that H2O on the surface will decompose to OH and H. It will also then, you could have another route where it reacts with a single atom oxygen on the surface, and you have 2 OH radicals. And these OH radicals then become the oxidizing element as opposed to oxygen. So then this oxidizes CO to CO2, and then you're left with 1 single hydrogen atom. We're doing this in a stagnation flow reactor. And the point is to minimize the problem to 1 dimension. And so these are all the objectives in the experimental side. From the simulation side, we want to improve the current models by using density functional theory data as opposed to a semi-empirical method like UBI QEP, for example. And we also want to include the recent surface science discoveries, such as the twin adsorption of CO. This is a schematic showing the reactor that we're using in the lab, and it's just 2 different depictions of the same reactor. If we focus here on the left, the idea is that gases would flow in from the bottom. They will go through a McKenna burner where we're not really burning anything. We're using this as a mixing device. Then gases will flow to the top. They go and hit a crucible where the rhodium catalyst is coated. And then with a sampling probe, we can go up and down in this direction, and then we can measure the chemistry. And so the whole point of this reactor is that we're minimizing the problem to only 1 dimension. Nothing is happening in the radial direction, it's all happening in the vertical direction. This makes simulations in ChemCon, for example, a lot easier, and then we can verify each step individually a lot more easily. And then here you have some things like a coil heater where we can control the temperature of the catalyst surface itself with a thermocouple from the bottom, and so on and so forth. What kind of data do we get from this reactor? You get profiles like this. The y-axis is the mole fraction of the chemicals or the chemical species you have, and the x-axis is the distance away from the catalytic surface. So if you remember from the depiction in the previous slide, we have the catalytic surface here, and as you go down close to the McKenna burner where we're mixing, we're going to the right in the x-axis. So at 0, we're at the catalyst surface. This is where you see O2 and CO being consumed, but you're forming a lot of CO2. And as you go to the right-hand side and you go far enough, you only see the feed composition, which in this case was 5% CO, 2.5% O2, and there's no CO2. There's no products because we're far away from the catalytic surface. We did this at 5 temperatures from 175 to 275, because again, we're targeting after treatment applications. And we did this at also 2 conditions. A stoichiometric condition, where we have 2 times the amount of O2 as CO. And then in lean conditions where you have, let's say that we're feeding the same amount, an equimolar amount of O2 and CO. From the simulation point of view, we use ChemCon Pro, and we have a license here at KAUST for the 2019 software, and the package is a stagnation flow, a CPD reactor. That's the package in ChemCon that we use. And the first thing we did before trying to come up with a mechanism is to see how the older mechanisms behave or fare against our data. And so I showed earlier 2 models that I highlighted, and these are depictions of how they fare against our experimental data. On the left-hand side is the model by Maestri et al. And you'll see here that 275 Celsius, we're seeing an under prediction of the reactivity. So if we follow these lines here, these are O2 and CO, we're seeing very small consumption as opposed to what we're actually observing in the lab. And same thing with generating CO2. So CO2 here is at 0.5%, whereas what we're observing is somewhere close to 5%, where there's an order of magnitude of difference. Then if we also look at the Cardenas model from Professor Duchman's group, and they obtain data in a stagnation flow reactor as well, we see a severe underpredictivity also of what's happening here, because at low temperatures like 200, we're not seeing any reactivity at all, whereas in the lab, we actually are forming CO2 when we're consuming CO and O2. We're currently going through the experimental data, and we're going then to transition to generating a model that predicts the reactivity at low temperature. And the plan that we have looks something like this. We will start with the DFT data. From there, using tools or linear relations like the group additivity, for example, or linear scaling relations if we're going from data for another catalyst, or PEP relations. From that, we can go to free energy of species and reactions. So we can predict some of the thermodynamics, and then we go from free energy to activation energy. This activation energy will be temperature dependent, and it will be coverage dependent, which is quite important, especially for CO chemistry. And then using transition state theory, we go to predicting the pre-exponential factor, at least with an order of magnitude approximation, but then we can also add the entropic effects. You put that together, and then we have a modified Arrhenius equation that is in the form of free energy, because we want to include the enthalpic effects, but also the entropic effects. We have not done that work yet, but this is for us the next step, so we can predict the reactivity at low temperature. So to end and summarize, CO oxidation is relevant at low temperature for after treatment applications. We saw some unpredicted reactivity at low temperature in the stagnation flow reactor. This is a reactor that we utilized in the lab for experimental data, and the idea is to minimize the problem to only one dimension. And for the future, this is the immediate next step we'll do, is that we want to improve the current models by using DFT data as opposed to semi-empirical methods. And then we include recent science or surface science discoveries like twin adsorptions for better predictability. Please allow me to thank you very much. If you have any questions, I'd be happy to answer those. And I would also welcome any feedback or suggestions. Thank you very much.
Okay, thank you very much for your nice presentation. Are there a question? So I would like to ask you, you told us that the model developed by Professor Vlachos and Professor Deutschmann did not fit your experimental data at low temperature. First of all, explain me maybe more detail in 200 Celsius is not very low temperature. And can you tell me the discrepancy with the models which developed earlier, and why do you need to develop the new one? Thank you.
Yes, so we're only saying low temperature at 200 because these models were developed at much higher temperatures, like 6.
Internal mass transfer resistances are minimized. In that way, we approach the intrinsic kinetics. It sometimes is very difficult to approach in a normal packet bed reactor where we have the lower size limit of conventional catalyst particles. So what is the research strategy in general in our efforts? We prepare different kind of catalyst. We check the coating techniques for microchannels. We characterize the catalyst with the standard methods. Then we do kinetic and thermodynamic investigations, mathematical modeling, and in some cases, even the product separation. Here you have a set of microreactors. You can see that almost everything besides the microreactor is still very macro, consisting of normal metal blocks and Schweiz lock fittings and gases. But there you can see the catalytic zone. There are 10 parallel small channels in one plate, and then we put about 10 plates on top of each other, and then we have a complete set of an efficient microreactor. We bought a commercial system from IMM in Frankfurt am Main in Germany, but we made ourselves the catalyst preparation and coating of the channels. So we focused on the chemical part. We also compared the performance with a tubular reactor. The whole reactor system is here. We put in the gases, helium, HCl, methanol to the microreactor, and then we have a neutralization bottle, and we take offline samples in this case. This hydrochlorination. In oxidation reactions, we have online gas chromatographic analysis. And in order to change the residence time to longer one, to get higher conversion, we coupled two microreactors in series, which is illustrated in this picture. Otherwise, it's completely the same as in the previous picture. What is then the catalyst? It has Lewis acid sites alumina, and the hypothesis is that HCl is absorbing and dissociating on aluminium oxide, and then also methanol or ethanol is dissociated, forming a methoxy or etoxy group, and then this methoxy group reacts with HCl, and then we can get the hydrochlorinated product. I will go back to this when I present the kinetic modeling. It turned out that the activity and selectivity could be improved by addition of zinc chloride to this catalyst. We tested also some zeolites. They were pretty active, but they showed quite much of deactivation. So, because of these instabilities, we remained with, from chemical sense, the classical neat alumina, because it was pretty selective and very, very stable and inexpensive. So that was our catalyst of choice. we had a binder-free slurry coating method. So we made a finely dispersed slurry of aluminum oxide. We treated the surface thermally to increase the surface roughness, put there the ball milled catalyst suspension, calcined, and so on. So you can see how small amount catalyst we have in one microreactor, only something like 3.4 milligram. So the benefit is also that in case of very valuable catalyst, you can operate with very small amounts of catalyst material. Confocal microscopy was used to characterize the catalyst and to determine the channel thickness, which was 15 micrometer. The channel depth was 90 micrometer, and this was then ready for kinetic and thermodynamic investigations, and then later on for mathematical modeling. So here is the reaction scheme. The reaction number 1 is the desired one. We want to make methyl chloride. But besides that, some etherification also happens. So we get dimethyl ether in reaction number 2. But luckily, some part of the dimethyl ether reacts with HCl and forms methyl chloride. So de facto, we have like, from kinetic sense, 3 reactions, but for thermodynamic sense, we have like 2 independent reactions in the system. The reaction is slightly exothermic. Main reaction has the reaction enthalpy about minus 30 kilojoule per mole. And you must see here that the reactions are not completely irreversible. Even the first reaction, the hydrochlorination, has a reversibility aspect because the equilibrium constant, which is a little bit less than 400 at 300 centigrade, does not give full conversion. It gives like 95% conversion maximally. Here you can see the performance of the microreactors. When we have one reactor, we get a reasonable conversion, but when we put the double amount of catalyst, 2 reactors in series, we can reach the thermodynamic limit, about 95% conversion. The selectivity behaves in an interesting manner. It actually improves with increasing temperature, as you can see, and with 2 reactors in series, we can reach selectivities which are like 97, 98%, which means that we get product of a very high purity. Here, based on the mechanism I rapidly sketched here, we made a derivation of the rate equations. We think that the absorption steps are in rapid quasi-equilibria, whereas the surface reaction steps are rate determining ones, and we take into account the reversibility of the reaction in all the rate equations from left-hand side to right-hand side, hydrochlorination, etherification, and hydrochlorination of the ether. Then the experience with the data indicated that the absorption of HCl dominates over that of methanol. Therefore, this term, absorption term D, is approximated to consist of the contribution of HCl only. So bottom line, how many parameters we have in one temperature to be determined? We have K1, K2, and K3, the rate constants, and we have the absorption constant of HCl, which is a reasonable amount of parameters. The equilibrium constants for each reaction are calculated separately from thermodynamic modeling. So then we don't need to determine from experiments in this case. Now I show a set of experiments which shows the efficiency of the microreactor. Look at the abscissa axis. The residence time in the reaction reactor is always less than 0.1 second. I think 0.05, 0.08 seconds, we already get a remarkably high conversion. And it improves very much when we increase the temperature from 280 to 400, 340 centigrade. The data are also rather accurate, thinking about that we were forced to use offline gas chromatographic analysis. Dimethyl ether is formed in very small amount. There is some scattering in the data, but observe that the scale is completely different for the dimethyl ether and methyl chloride. So we then obtained the activation energy for methyl chloride formation, and it was double amount compared to the previously published activation energies. And this suggests that internal diffusional limitations have prevailed quite strongly in previous investigations done with packet bed reactors. So therefore, we developed the reaction diffusion model in order to describe the diffusion inside the pores and to play with different catalyst layer thicknesses and see which role the diffusion might play if we increase the thickness. And here you see in this picture very clearly 15 micrometer. There we have a very flat profile when we have 15 micrometer of the thickness of the porous layer, like we have in microreactors. We have very high effectiveness factor, increasing 0.9, in some cases even close to 1. But then when we go up to thicker catalyst layers or bigger particles, you see like 100 micrometer diameter and 200 micrometer, the curve, the concentration profile is really strongly curved, strongly decreasing. That means that remarkably big concentration gradients appear even in so small particles. Not to talk about particles which are of the amount like 500 or 1000 micrometer, 1 millimeter in diameter. Then we have really only the outer layer of the catalyst in use. So all that we avoid by using microreactors. You can see conventional fixed bed, the effectiveness factor can be 0.1 to 0.06, for example. So that means that by using microreactor, we can make 10 times smaller reactor, bottom line, roughly speaking. So here you see the great benefit for this type of system. And also you see that using very thin catalyst layers, which are possible in microreactors, is the only way to approach the intrinsic kinetics in a reliable manner. I don't have time to talk very much about ethyl hydrochlorination. I just mentioned the reaction scheme. It's a little bit more complicated than methyl hydrochlorination. We get also some acetaldehyde, a little bit more side products, but I can show also here the mathematical modeling shows very well how the things are happening when we convert ethanol with HCl to ethyl chloride. So, here we then made the similar type of kinetic model as we did for methyl chloride, but we included some additional reactions like formation of ethane and acetaldehyde, and then we got quite good model fit into the system. So let me conclude. Microreactor suppresses severe diffusion limitations in methanol and ethanol hydrochlorination, leading to a very dramatic decrease of the reactor size to very excellent process intensification. We developed detailed kinetic models for both methanol and ethanol hydrochlorination, and we also managed then in separate experiments demonstrate that we can make by condensation very clean products, for example, 99% methyl chloride, just to condense away the water and unreacted methanol. I would say that microprocess technology is a great challenge. It's strongly multidisciplinary, where we have everything from manufacturing and characterization to screening, kinetics, thermodynamics, mass and heat transfer, flow measurements, etc. One should take the challenge and search always for new applications. Here is the team at Industrial Chemistry and Chemical Reaction Engineering. Last year, our laboratory had the 100th birthday. Thank you very much, all the audience in Milano, Novosibirsk, all over the world.
Thank you, Professor Salmi, for your very interesting presentation. Other questions? So, Professor Salmi, I would like to ask you, you tell that the application of microreactors allows to avoid diffusion limitations, but you also tell us about the internal diffusion limitation. So, how it will affect?
Yes, actually here we had microreactor where we had very thin catalyst layer, like 15 micrometers. So that means that diffusion limitation was very small in the pores. Effectiveness factor was much more than 0.9. So it is possible, and it's thanks simply to the thin layers. And the challenge to diminish the diffusion limitation is always high when we have gas phase reactions at high temperatures, when the reaction rate is very rapid.
Okay, thank you very much.
In the microreactor, we operated in the level of intrinsic kinetics, but not in the, we also compared with classical packet bed, and there we had heavy diffusion limitation for this system because the particles were on the hundreds of micrometers or something like that.
Okay, thank you very much. Are there more questions?
Can I ask a question?
Yes.
Hi, this is Professor Kopczynski, Montreal, McGill University in Canada. Thanks for the nice talk. I hope you can hear my question. So the model that you assumed was the plug flow model, I think
yes.
You mentioned, but you also achieved rather high conversion, and you only do an in and out. So you only measure essentially concentration at the outlet. But how can you make sure, especially at high conversion, that what you really have is really what you have inside. So what I'm getting at, when you have a differential model, you usually want to have very low conversion, right? But I assume you used an integral approach to integrate even over the mass of the catalyst in order to describe even at high conversion the reaction progress.
Yes, I think it was a pseudo-homogeneous model. So the classical plug flow model was integrated for each and every experiment from inlet to outlet, and then we compared the model prediction at the reactor outlet with the experiments, because we cannot take samples inside the microreactor. We only see the outlet, but we tried to make it in a very correct and orthodox way. So we used always the full plug flow model, not any kind of differential reactor model or something, because we had quite some high conversions in many experiments.
Yeah, what were the mass flow rates you had? Because with your, I don't know, if maybe a millimeter lengths, the channels, or even less, and 3 milligram of catalyst and 0.01 second residence time, what were the flows?
I don't remember exactly the flows now, but I think we have published this work in Chemical Engineering Science journal, so you could have a look. The exact data are there.
Okay, maybe one last point. You mentioned also a little bit exothermic, but you assumed it's all isothermal in your model. That's correct?
Yes. That's also a critical issue, but we tried to evaluate the heat. But you see, this is inside a heavy metallic block, which actually is heated up. So I think the metal block around the microreactor is more or less determining the temperature there. But your point is of great interest, particularly if you have systems which have higher reaction enthalpy.
Okay, thanks so much.
Are there more questions?
May I ask? Hello?
Yes.
Can you hear me?
Yes.
Yeah, Gunter Kolt from Fraunhofer IMM in Germany. I'm asking, what do you think about applying a differential reactor, such as a recycle reactor, for such kind of investigations? Wouldn't that allow even more precise determination of the parameters?
Probably not, because I think here we can have a very broad interval of the concentration and conversions, because I think for determination of intrinsic kinetics, it's important that you operate with a broad concentration intervals. So I think that this straightforward system, you measure at the outlet in continuous mode, and you have plug flow model, or you can even put axial dispersion model, might be in any case the best one, even if it's of course requires a lot of computation, but it's not a problem nowadays.
Okay, thank you.
Are there more questions? So Professor Salmi, thank you very much for a very nice presentation. And just now we have a coffee break, and so our sections. Thank you all participants, all those who presented their presentation, and now have a small rest. Thank you very much.
Thank you. Thank you.
Yes, it is.
Yes, it is.
And can you hear me?
Yes, perfectly, Andrei.
Oh, very good. Okay. So it seems to me that's already time we can start, right? I hope so. So, dear colleagues, hello. I am very happy to see you all here, to see all people who I see and a lot of people who I don't see but who are present now currently in our Zoom. I'm starting this opening not because I'm the most important person here, it's just something like a dispatcher who will give the words to people to make some introduction speech.
I don't hear anybody. I don't hear Andrei.
Mm-hmm. Well,
Enrico, do you hear me? Yes. I don't hear. Can you unmute and then I can see whether I hear you or not?
Guy, can you hear me?
I don't hear you.
I can hear you. And I can hear everybody else as well.
Yeah, I can also hear him and I can also hear everyone else.
Mm-hmm. Okay. Sorry, I think we have to go on. Okay. So yes, now we'll start the opening procedure and maybe Matteo Maestri will. Okay, thank you.
Yeah.
So maybe Matteo Maestri will also say a couple of words before our introducing speeches. Matteo, as also one of the main organizers of this conference, please say a few words.
Okay, so thank you, Andrei, and dear colleagues and friends, also my warmest welcome to Chem Reactor 24. So I think that together with Andrei and the rest of the committee, we have finalized a very interesting scientific conference from fundamentals to latest application in several fields. Therefore, I wish you an exciting and fruitful conference, and I look forward to the rest of the meeting. Thank you.
Thank you. So now I think we can start the real opening procedure. And the first, I would like to dispatch to forward the word to chairman of the International Scientific Committee of our conference, who is a traditional chairman of this scientific committee for many years. To Professor Parmon, in fact, he was not able to be present here in real time, let's say so, but so we have a recording of the speech. So Tatiana, can you please switch on the speech of Professor Parmon?
Dear friends, colleagues, ladies and gentlemen, this is a large pleasure for me to participate at the opening of the 24th Conference on Chemical Reactors, Chem Reactor. Well, it is an honor for me to be in contact with this conference for many, many years. I would like to remember that this conference was arranged firstly in Soviet Union as typical, not very large domestic national conference. But nevertheless, the topic of the conference was so interesting and so attractive that step by step in our conference, Chem Reactor, international partners were participated, and step by step this Chem Reactor conference started to be international conference. We have experience to arrange it not only in Russia, in some cities of Russia, but also in other countries. And in the history, we arranged this conference in Helsinki, Berlin, Athens, Crete, Malta, Vienna, Luxembourg. The geography of participants was also very large, and now we hope that the attendees will be from 50 countries. Indeed, the problem of basic research in the area of constructing and designing catalytic reactors and chemical reactors as whole is very wide and very important for many applications, many practical applications, not only for theoretical training. Indeed, we were very glad that some well-known universities throughout Europe helped us to arrange this conference. For example, Delft University of Technology in the Netherlands, University College London in the United Kingdom, Ghent University in Belgium. Now we had the honor to be invited by the eminent university Politecnico di Milano. Unfortunately, the well-known situation with COVID did not allow us to collect us together in one place, and many events of our conference will be arranged by special technical systems. But nevertheless, I believe that it did not prevent very serious discussion, conversations, new contacts, and so on. So I would like to wish the very good results of our conference, and indeed we would appreciate to discuss possibility to continue these conferences in other cities or other countries. Thank you very much.
Okay, thanks to Professor Parmon for this speech. As he already said that this conference would be impossible without such a significant and very helpful, efficient partner in our conference, Milano Politecnico. Of course, people from Milano Politecnico made a great job on preparation of this conference and provided very excellent bunch of contributions to this conference. So I would like now to give the words to representatives of Milano Politecnico. Maybe I think the first one, maybe to a choice, but it seems to me that I would prefer to give the word first to Enrico Tronconi, who is a participant of Chem Reactor conference for many, many years. Enrico, could you please say a few words?
And thank you, Andrei, for the invitation, and dear colleagues. On behalf of the Catalysis and Chemical Reaction Engineering Group at Politecnico di Milano, it's my great pleasure to welcome you all, even though virtually, to Milano for this exciting new edition of Chem Reactor Conference. And in fact, our group is very proud of being part of the scientific organization of Chem Reactor 24. And in this regard, I would like to express my appreciation to Professors Giampiero Groppi and Matteo Maestri, and to all the colleagues and friends from the Bracconi Institute who have made an exemplary effort in putting together a very, very nice scientific program for this conference. And on this occasion, however, I would like also to spend just a few words in memory of Professor Pio Forzatti, who passed away last July. Pio was not only the founding father of our group in Milano and our mentor, but he also was the one who first established close connections between Milano and the Chem Reactor community. At the end of the last century, Pio was one of the few foreign participants in the conference, which at that time was still held only in Russia. And after that, he was for a long time a member of the International Scientific Committee of Chem Reactor. So I'm positive that he would be very pleased with the excellent scientific program of Chem Reactor 24. And now I just want to wish you all a stimulating and very successful conference.
Thank you very much for your speech, Enrico. It's very good. Thank you.
Thank you.
And of course, now I would like to propose to say some few introducing words to another person who did a lot for Chem Reactor conference in general, and especially for this Chem Reactor 24 conference, Professor Gianpiero Groppi. Please, Gianpiero.
Thank you, Andrei. Good morning or good afternoon, ladies and gentlemen, depending on your time zone. First of all, let me say that it would have been a real pleasure to host Chem Reactor in Milano, also because September could be a very nice period here. And actually, the weather today is really fine. However, this was not possible under the present circumstances, and we are equally honored and delighted to assist our colleagues from the Bracconi Institute in organizing the 24th Chem Reactor Conference by remote. Professor Permon have already illustrated the historical importance of this conference in the chemical engineering community, and more specifically in the chemical reactor technology field. I don't think it is necessary to add further works, except for my personal involvement as an enthusiastic participant to previous edition of Chem Reactor. Conference, as you have seen in the program, has been structured in 4 different topics, ranging from the chemical reaction engineering fundamentals to the experimental and theoretical methods for reactor design and scale-up, and to the advanced reactor concept based on non-conventional source of energy, on novel structural geometries, and on multifunctional integration of reaction and separator step. It's an honor to welcome at the conference, although regrettably not in Milano, all the plenary speakers and the keynote lecturers that accepted our invitation to provide top-level contribution. We will cover most of the key topics of the conference. I'm confident that the high quality of their presentation will boost the discussion in the different thematic sessions all along the conference. Finally, let me thank in advance all the attendees for their active participation, and our colleague from the Bracconi Institute for the impressive efforts they made to organize such a high-level international conference under these difficult circumstances. Enjoy the meeting.
Okay, thank you very much, Gianpiero. Okay, we have some time. I would like maybe to, before our next lecture, to give some introduction, maybe some statistics information about our previous Chem Reactor conferences. Can you see my presentation?
Yes.
Yes.
So,
yes.
From the beginning. So just some introduction, statistics, some information about these conferences. So this is the Chem Reactor number 24. As you, of course, already know, arranged this time by CHETEROGENEOUS Institute of Catalysis in Novosibirsk and Milano Politecnico in Milan, Italy. The history. So the conference statistics, we actually tried to calculate how many people in general participated in all these events for all these years. It's definitely, I think, few thousands, including more than 1,000 participants during maybe the last 10 conferences. You can see here the map of the world. So the green is the points where the conferences were already held. I should say it's maps from some previous events. So Italy is not colored here in green. I think we will do it in the closing event of the conference. But you can see that a yellow color means participants. So you can see that practically we already involved more than 50 countries during the whole history, and at each conference we approximately have something like 200 participants from more than 30 countries, but in total we have more than 50 countries, and involving practically all parts of the world and all continents except maybe Antarctica. So something wrong is with Antarctica, and all other continents are participating. Here you see the list of these conferences, starting from events in the end of last century, which were held in Russia, but it's already starting from 1996. There were some international participations provided since that time. And you see that from this century, from the year of 2001, we started to arrange these conferences in Europe. In Helsinki, then in Berlin, Athens, Malta, Vienna, Luxembourg, Delft, London, Ghent, and now theoretically Italy, and unfortunately, just theoretically, practically, we are online in our heavy conditions. But I guess this conference, so of course, Italian Milano Politecnico did a very great job to arrange this one conference. And one of the most important traditions of this conference is the lecture dedicated to the memory of Professor Mikhail Slin'ko, who was a founder of this conference and very significant scientist in Soviet Union and Russia. You see the list of all activities, all his works in chemical engineering. Maybe very briefly, I can say that he was one of the first persons who implemented the chemical reaction engineering as active participations of modeling methods. And it was a great step forward, not only in domestic scale, but he was possibly one of the persons worldwide to start this very interesting and promising area. Starting from year of 2008, so it was decided to establish the honorary Slin'ko lecture, and it was decided that for each chem reactor reaction, each chem reactor conference, it was decided that the right to present this lecture at each conference will be given to the world recognized experts in the field of chemical reaction engineering. This person is traditionally selected by the members of the International Scientific Committee. This is the list of people who already, the first one lecture was made in Chem Reactor at Vienna, Austria. The first one was read by Professor Matros, who was actually the student of Professor Slin'ko. Then in Luxembourg, we had a lecture from Andrzej Stankiewicz. In year of 2014, we have even 2 lectures because it was the anniversary. It was a special year. It was the 100th anniversary of Professor Slin'ko, and there we have 2 lectures. You see by Jakob Moulin, Frick Kaptein, and Javier Perez Ramirez, and another one by Dan Lass. In 2016 in London, Gilbert Farmat provided a Slin'ko lecture, and at the last event until our conference in Ghent in 2018, this lecture was provided by Jans Norskov. And so this was a very brief introduction of this tradition, and the following okay, and now we still have some time, but I guess we can softly transfer to we will have this memorial Slin'ko lecture right now in a few minutes. The only thing that I want to say now, of course, we will have afterwards, we will have the closing procedure, and we will maybe talk again and discuss the results of our conference and exchange our opinions about it. Currently, at the moment, I would like only to wish all participants, first of all, to express my gratitude to all participants who decided to participate in this not easy time. I see the attendance is very good, very in quality and in quantity. So it seems to me we have very good perspectives for this conference. And I would like to wish all participants to present their contributions in the optimal way and receive the maximum use of this conference and maximum positive knowledge, emotions, contacts. And so all good, I wish all people good luck, and I would like to transfer already the word to chairman of our next session, Professor Dmitry Murzin and Professor Tapio Salmi.
Be which time 11 at UTC. So yes. I think we should probably wait for some 5 minutes for other people to join.
Okay. Yes.
Would it be the best solution? Because
yes. Okay. Let's wait for 5 minutes.
I think we just wait for 5 minutes and then we will start.
Thank you. Okay.
Together with my excellent colleague, Professor Murzin, and we are very curious about to listen to the first plenary lecture. So soon we are starting.
Where are you, Tapio?
Where?
Where are you?
I am in the seminar room which has the name rubidium. You know, the alkali metal. Rubidium is the name of this seminar room. We have moved to this building a few weeks ago, completely new building.
Tapio and Dimitri, I just want to say that my computer was hacked 1 hour ago. So I had to do all kinds of things to be able to join in time. I'm a bit nervous because it was hacked from, and my university told me it was from Germany. And then they kicked me out because there was a danger of contamination. And I just managed to join half an hour ago again.
Was it your laptop or?
My laptop, yes. Everything is okay.
Now you're back to normal life. I think we will start in really a couple of minutes.
In this couple of minutes, maybe I will say also some words that we are very grateful also for preparation for arrangement of this conference to Ilios company, who is already our partner for many Chem Reactor conferences and who also did a great job in preparation of Chem Reactor 24.
Professor Slin'ko is a very respected figure in the field of chemical reaction and chemical reactor engineering. He himself was a physicist by training, but starting from his very young years was exposed to chemical technology and chemical engineering, was a veteran of the Second World War, and then started to work at the Karpov Institute of Physical Chemistry in Moscow in the laboratory of technical catalysis together with Professor Boreskov, and both of them moved to Novosibirsk at some point, where Professor Slin'ko was a deputy director, and where he initiated research in the field of chemical reaction and reactor engineering. He was very instrumental also in applying mathematical models for chemical reactor engineering. And he was also the person who, in fact, initiated the whole series of chem reactor conferences. At first, they were organized mainly in the former Soviet Union, and then 2001 was the first international emission of that conference, which actually was held in Helsinki. And one of the plenary lectures was given by Professor Slin'ko together with a second person. It was actually me. So there were two plenary speakers at that conference. And the reason for us somehow being associated together was that Professor Slin'ko at some point kindly agreed to be an opponent of my habilitation thesis. And then later on, we even published a couple of papers together. He was an amazing gentleman. At the age of 85 or 90, he was able even to derive second-order differential equations, and they just came out of his head without any problems. So some time ago, the organizing committee of this international scientific conference, Chem Reactor, decided to award or establish the Professor Slin'ko honorary lectures. And there were several already awardees of this type of award. And now the lecture will be given by a famous professor in chemical engineering, chemical reaction engineering in particular, Guy Marin. And I hope that my colleague, Professor Salmi, will say a few words about Professor Guy Marin. Tapio, the floor is yours.
Thank you. Good afternoon to everybody. Guy Marin comes from the Laboratory of Chemical Technology and the Center of Sustainable Chemistry at Ghent University, Belgium. The scope of Professor Marin's research is very broad, from chemical kinetics and chemical engineering, aimed at the modeling and design of chemical processes and products from the molecular level up to industrial scale. He is member of the Royal Flemish Academy of Belgium for Sciences and Arts, and he has got very many recognitions on the international level of chemical engineering. For example, he has given the P.V. Danckwerts Memorial Lecture in Chemical Engineering and Kinetics. Professor Marin is co-author of 2 books and author and co-author of more than 700 original articles in high-impact journals. He is also a co-editor of the very prestigious journal, Chemical Engineering Journal. So at this moment, it's my great pleasure to invite Professor Guy Marin, one of the greatest scientists in chemical reaction engineering, to give the first plenary lecture of this Chem Reactor conference. Dear Guy, the floor is yours.
Thank you, Tapio. Thank you for the very nice words. But I would like to use my own slides. So the slides that are shown now are those of yesterday, and I did make some changes. And I would like to be able to use my most recent version and to share that with you. I did call Tatiana to ask her to do that.
Probably you can also request the remote control when you see clear view options. Maybe
I cannot start screen sharing while somebody else is sharing.
Yeah, so, I think you should go to view options and then request remote control.
That's what I did now. I still cannot start sharing my screen.
You should then ask the technical assistance.
Yes. So I'm still seeing Tatiana's screen.
Andrei.
I'm trying, yes, I'm contacting technical people. So you already uploaded your presentation, right? Or not?
Yes, but it's no longer the most recent version, and I would like to have full control of my slides.
Yeah, so the best is that you will be allowed to have the control.
Алло, что там? Да, он просит поставить более свежую.
I think I will start. First of all, I would like to thank all of you, and in particular the scientific committee, to give me the honor to give this presentation. I feel very humbled by having this honor, and I'm always have been very, very much impressed by the work of the Soviet School of Chemical Engineering in general, and catalytic reaction engineering in particular. I want to organize my talk as follows. I will first of all give an overview of what I consider being the challenges for our field today, and also the corresponding opportunities. And then I will address the issue related to raw materials on one hand and energy on the other hand. The times are changing. Until quite recently, we were used to use fossil fuels, natural gas, coal, crude oil, in order to come to useful products. and the process industry has done a very great job in doing so. But this was done in a linear way. That means that we did not really worry about the end life of our products, nor about the CO2 emissions. So we want to change from this linear type of economy to a circular type of economy. And in particular, we want to either start using renewable feedstocks like biomass or plastic waste and waste in general to come to the useful services and products that are of interest to us. Circular economy can be realized by 5 types of loops. And if you utilize all of them, a Dutch recent study has shown that up to 70% of the European chemical industry products can be recirculated. In what comes, I will focus on 3 out of these 4 loops. I will focus on renewable raw materials, on chemical recycling, and on energy recovery and carbon utilization. Climate change and hence energy is a crucial thing next to the choice of raw materials. What is shown here is on the left a conventional technology to establish the high temperatures needed for a lot of the chemical process industry processes. This consists of basically having the reactor suspended in a gas-fired furnace. And on the right, you see an alternative, so-called electric heating, which is relying on the Cheula effect to establish the desired temperature. And of course, this would help to tackle the climate change challenge by having only if we could really manage to have electricity which is cheap on one hand and also green on the other hand. One other way of coming to a solution for the climate change is indeed to start connecting different industrial sectors with each other. In this slide, I show the sector consisting of treatment of waste, organic waste from agriculture by anaerobic digestion, which produces, as you know, a mixture of methane and CO2, and which after some separation leads to biomethane, which can be injected in the existing natural gas grid. And then you can imagine that you can combine this biomethane with the CO2 point emissions in order, for example, to convert the CO2 into CO, and next using CO as a new chemical building block. What are the opportunities provided by these challenges for our field? Well, that is what I will discuss next, and you can all of them put them into the category of process intensification. And I've shown here 2 former awardees of this lecture who have been advocating very early on process intensification. Chemical engineering and hence also process intensification involves a very broad spectrum of length and timescales. And we start from molecules and go up to the size of particles, catalyst pellets, for example, come to the size of a reactor, a complete plant, and then a full enterprise. The voie royale to handle these these huge length scales, spectra, and timescale spectra is highlighted in this slide. Important to stress is here that you want to be able to combine laboratory data with ab initio calculations. And this leads to what you can call microkinetic models. That means kinetic models which are not simple empirical rate laws, but which correspond to insight into the reaction mechanism and are based on all the elementary steps that are involved in transforming a molecule into a useful product. And once you do have this type of microkinetic models, it is sufficient between quotation mark it is sufficient between quotation marks to apply the conservation laws of momentum, mass, and energy in the form of computational fluid dynamic models to come to process and/or product design. Let me go through this step by step. For example, and this is an example of ab initio calculations of steps involved in the conversion of alcohols catalyzed by zeolites. Can you get the full screen? Is this? I see only now. I don't no longer see a full screen. Can somebody?
Maybe. It's possibly on your side. Is it possible? How you usually turn on the full screen in your presentations?
Yeah. Okay. There it is. Yeah. What is shown here is an ethanol molecule interacting with an acid site of ZSM5 in this case, and being adsorbed. And we can calculate with density functional theory the corresponding equilibrium, adsorption equilibrium coefficients and the rate coefficients. Another important aspect that is popped up in the last decades is several huge advances in experiment techniques. One of them being, for example, so-called two-dimensional gas chromatography, where you separate complex feedstocks based not on one property, but on two preferentially orthogonal properties, like volatility on one hand and polarity on the other hand. I should not forget to mention also the huge progress that has been made concerning the techniques allowing to characterize catalysts even during a reaction. Microkinetics is accounting for all the elementary steps involved in the chemistry that is relevant. So at first sight, you would think that this requires the knowledge of the kinetic rate coefficients of thousands of reactions. But fortunately, it turns out that by looking at the elementary reaction step level, you very quickly realize that you can describe this full chemistry by identifying a limited number of elementary reaction families. For example, like on the bottom of this slide, beta carbon-carbon scission. And hence, you can limit the ab initio calculations of the elementary step kinetics to an ab initio calculation of heads of reaction family. And once you have identified these elementary reaction families, you can translate this identification into chemical rules, and you can translate these chemical rules into algorithms which allow to generate fully automatically the full reaction network. And of course, in order to do so in an efficient way, you have to take advantage of all the commercially or freely available software packages combining the know-how in the field of computer sciences, chemistry, and mathematics, and allowing advanced species representation and, very importantly, unique species representation, which can be even three-dimensional and even take into account of chirality, and which is based in principle on substructure and matching. And then computational fluid dynamics is, of course, a booming field. with the toolkits which are more and more user-friendly and available for everybody. You can, of course, do this in a rather rough way, which corresponds to Reynolds average Navier-Stokes modeling. You can do it a little bit more sophisticated by so-called large eddy simulation modeling. And the most sophisticated one is a direct numerical simulation. For reactive flows, runs are very often used, and more also large eddy simulations. And as you can see on this slide here on the bottom, the more expensive your CFD technique, the more detailed you can simulate reactive flows. And then this combination of elementary reaction kinetics on one hand and sophisticated computational fluid dynamics allows you to come up with a computer-aided reactor design. Shown here are two examples. On the left, this is the inside of a cylindrical tube with inserts. So there is there a rep added to the internal surface of the reactor wall in a discontinuous way, and creating eddies which are beneficial for heat and eventually for mass transfer. But as we will see later, detrimental when it concerns pressure drop. On the right, you see a so-called vortex reactor, which is a type of reactor that we have been investigating the last decade at Ghent University, and which consists of a rotating bed of a gas of either biomass or catalyst pellets. These pellets, or this powder, is brought into a rotating movement by feeding tangentially gas to this bed. This leads to a centrifugal force which is maintaining the fluidized bed inside the reactor, despite the very high gas slip velocities. This very high gas slip velocity allows a very good, very intensified gas-solid heat and mass transfer. On top of that, the fluid bed character of the rotating bed leads to a high effective thermoconductivity of the rotating bed, which offers a lot of advantages with respect to heat management. There too, of course, the combination of modeling and numerical simulations with experimental data is very important. What is shown here, and I would have liked to be able to show you the rotating pine wood pellet there on the left. We combine this in a cold flow experiment with the particle image velocimetry determination, leading to, as a function of the distance from the reactor wall to the central exit, to experimental values for the tangential or the azimuthal velocity. On the left of this slide is shown a CFD model calculations of this azimuthal particle velocity. This is, of course, only a piece of the circle. And what is shown on the right is a simulated on one hand and an experimental field of the azimuthal particle velocity. And as you can see, the models that we have been employed for this validation indeed allow a good correspondence between simulated velocities and the experimental velocities. So having gone through the challenges on one side and the opportunities and the available toolkits, tools for chemical reaction engineers, I will now try to show how we apply this to the conversion of raw materials to useful products. And I will start with the conversion of bioalcohols. And on this slide, by means of biobutanol. So biobutanol can be obtained by biotechnology techniques from biomass in general and waste in particular. And then it's up to us chemical reaction engineers to convert this biobutanol into butenes. Of course, in order to do that in an efficient way, we have to understand in detail the chemistry and the catalysis of this dehydration of biobutanol to butenes. This slide shows you the different paths that are possible and that do occur in this conversion of butanol to butenes. I will make it simple to focus only on part A, the conversion of 1 butanol to 1 butene, and I will show you results of ab initio calculations. What is shown here for part A alone are the different elementary steps and highlighted on the right a transition state for one of these elementary steps. And we have been doing this calculation for all these elementary steps. And we have obtained, hence, corresponding Arrhenius parameters allowing to understand the effect of the catalysis of the zeolite type on one hand and the effect of process conditions on the conversion of 1 butanol to 1 butene. We have done a similar exercise for bioethanol, and we have been able to compare our ab initio determined microkinetic model with data provided by industry in the form of a USA patent, where are reported data on a unit producing 220,000 tons of ethylene per year in 2 adiabatic reactors with heating in between the 2 adiabatic reactors. And what is shown here are the ab initio calculated ethanol conversion ethylene yield and the temperature throughout the 2 beds, and also by ways of symbols, the reported yields and conversions and temperature. So, and this without adapting any kinetic or thermodynamic parameter to the reported experimental data. So the take-home message here is that indeed today we are capable of accounting for all the scales that are relevant for a heterogeneously catalyzed process, from the scale of the active site via the scale of the pores, of the crystallites, of the pellets, and of the reactor. And this should allow us to indeed combine design of a catalyst with optimal design of a reactor. The second example of application is related to CO2 as a raw material. And this is commonly known today as carbon capture and utilization. What is shown here is, on one hand, on the top, the total amount of CO2 emitted by industry, so-called point emissions, and on the other hand, the production of biomethane by this anaerobic fermentation of organic waste I have been referring to in the beginning of my talk. And if you manage to produce out of these 2 streams CO, you can combine it with hydrogen, preferably, of course, green hydrogen, to indeed produce the full spectrum of molecules that we are using today. And I will focus on this so-called super dry reforming process that indeed is converting 3 molecules with 1 methane molecule to 4 CO molecules and 2 water molecules. And this in contrast to dry reforming, which is only converting 1 CO2 molecule per methane molecule. And the trick here is that we have, in the process that we call super dry reforming, avoided the water gas shift reaction. How does this super dry reforming process operate? Well, it is a cyclic process. It consists of 2 steps. In the first step, we bring into contact methane and CO2 via nickel, which converts it into CO and hydrogen with iron oxide. And this CO and hydrogen is reducing the iron oxide into iron while producing water on one hand and the CO2 molecules on the other hand. But the CO2 molecules on the other hand, in black there on top of the square shown, these 2 CO molecules together with the supplementary 2 green CO2 molecules on the right hand side are, as they are fit or as they are formed, immediately absorbed on calcium oxide, which is also present in the reactor, and transform the calcium oxide into calcium carbonate. And as soon as you are afraid of having breakthrough of CO2, you switch from step 1 conditions to step 2 conditions. You start, but maintaining the same temperature. You start then the blue step, which is converting the calcium carbonate back to calcium oxide, liberating CO2 molecules, which have a sufficient oxidating power to reoxidize whatever iron that has been formed during the reduction of the iron oxide into iron oxide. Hence, in this process, we close the 2 loops, the redox loop of iron and the carbonation-decarbonation loop of calcium, while producing in the first step water and in the second step CO molecules. This means that this is a dynamic process in principle, but by putting the same materials not in 1 reactor but in 8 reactors in parallel, and operating each of these 8 reactors in such a way that they are in different stages of the cycle, you obtain time average wise a steady stream of water, pure water on one hand, and a steady stream of pure CO on the other hand. And this is really today called chemical looping, but it is only one example of a transient operation of a fixed bed reactor, like for example the reverse flow reactor advocated by Matros, the first awardee of this plenary type of lecture. I will go on with methane as a raw material. Methane, which obviously today is typically natural gas, fossil, but it can also be more and more the biomethane I was mentioning before. And I will briefly take the opportunity of discussing oxidative coupling of methane to C2 products, preferably, of course, ethylene, to introduce the concept of catalyst descriptor. There are 3 types of challenges for oxidative coupling of methane. There is the heat management issue, because it's an overall very exothermic reaction. There is the selectivity issue, because of course you form CO and CO2 as a side product. And there is the fact that methane is very inert, so that you need high temperatures to activate methane molecules. And these temperatures are so high that you cannot neglect gas phase reactions. Even in the presence of catalysts, you better account for gas phase reactions. What are shown here are all the possible gas phase reactions when you combine methane and oxygen at the temperatures, let's say at 700, 800 degrees C. The red ones, those with the red label, are desired ones, if you want, and in particular the coupling of methyl radicals. And it turns out that this mythical radical coupling is indeed the desired reaction that you want to favor by adding to the gas phase also a catalyst. The main function of the catalyst being indeed, and that's the very first reaction on the left of this slide, the main function of the catalyst being indeed the generation of middle radicals, which then subsequently combine in the gas phase to C2 products. What is shown here are, again, different elementary steps. Those in red are desired steps. So the catalyst is having functions there which are favorable for high conversion and high yield of C2 products. But typical catalysts also have undesired effects, which are corresponding to the elementary steps that are highlighted here in black. Highlighted with the arrows, the big arrows, are the kinetically significant steps on a particular type of catalyst, tin lithium magnesium oxide. I want also to stress the concept of elementary reaction families. So there is plenty of elementary steps here, but there is only a limited number of elementary reaction families that are involved, and hence you need to determine only the values of rate coefficients of a limited number of elementary reaction families. And you can do this type of microkinetic modeling for different types of catalysts. And as you can see, you can adequately describe the conversion of methanes, oxygen, and the formation of C2 products on a broad range of catalysts. And this is important, without changing all the kinetic parameters in the microkinetic model. Because we do distinguish in the microkinetic models that we have developed for oxidative coupling of methane and that we have developed in general to applied to other types of reactions too. We distinguish, and others of course have done this too, we distinguish between so-called kinetic descriptors, which are more or less independent of the catalyst, and catalyst descriptors, which are the values of which are very strongly determined by the catalyst, and which of course then do determine the catalyst performance. Here are the four most important catalyst descriptors. It's the reaction enthalpy of hydrogen abstraction from methane, so the methane activation and the formation of middle radicals, the chemisorption heat of oxygen, the sticking probability, and that's a black one, so that's something you want to be as low as possible. Yeah, the sticking probability of middle radicals on the catalyst surface, basically, and then an obvious one, the total concentration of active sites. And depending on the values of these catalyst descriptors, you end up with the active catalyst, the green one, less active catalyst, the blue one, the lithium magnesium oxide, and then highly selective catalyst, the red one, the sodium, manganese, tungsten, silica catalyst. And by playing of these values of the catalyst descriptors, you can, at least in theory, come up with an optimal catalyst formulation, which corresponds to optimized values of the catalyst descriptors, which are, and an example of which is shown on the bottom left of this slide, where you have shown, where they are shown on the z-axis the yield for C2 products as a function of two of these four catalyst descriptors, the oxygen chemisorption enthalpy and the enthalpy for the hydrogen abstraction from methane. And you can see that there are clearly distinguished peaks which give much higher yields than those obtained with high other values, non-optimized values of the catalyst descriptors. So the take-home message here is that the microkinetic models that you develop can be used to come to a model-guided catalyst design. The next raw material I will discuss, and that's of course very important in the context of plastic waste, are in the context of circular economy rather, is plastic waste. And this is the loop 4 of the 5 loops that I have been showing in the very beginning of my talk. What you see here is you start from the top left with plastic waste, and then you end up with products. One of the products being the naphtha loop oil wax on the right of this slide. This naphtha loop oil wax can be analyzed with GC and GC techniques, as discussed in the beginning of my talk. And the light green part of this fraction is the one that is most interesting as a possible source for the production of light olefins. The orange one on the bottom right is causing problems and can eventually lead to coke formation. Well, is this reasonable? Well, in order to evaluate this, we have been, in order to evaluate whether we can add plastics next to the classical feedstocks shown on the left of the slide to a steam cracker for the production of the products that are shown on the right of this slide. Well, we have been performing experiments in the pilot plant that is available at Ghent University. And it is a gas-fired pilot plant with a very sophisticated online analysis section. We have a very long history, which started with one of the other awardees of this Slin'ko lecture, Gilbert Froment, in the 70s, and has been evolving since by improving continuously the pilot plant and correspondingly improving the microkinetics models. Microkinetic models which ultimately have led to the commercialization of computer codes with a graphical user interface, which is very user-friendly, and which is today, or since 2015, commercialized by a spin-off company, AVGI, of Ghent University. And indeed, this is a summary of the test in this pilot plant, where you see that indeed with plastic waste feed, you can obtain very reasonable yields of the desired olefins. But note on the bottom that you do make more coke with that feed than with the fossil naphtha feed. And this brings me to the energy issue, and discussing the energy issue, the energy challenge. I will do that by discussing steam cracking. Steam cracking is indeed a very energy consuming process. You need temperatures which are higher than, way higher than 800 degrees C. The reaction is on top of that very endothermic. So you need, in order to reach these temperatures and maintain them, you need to suspend the reactor coils in a gas-fired firebox, shown on the bottom left of this slide. The scale is huge, as you can see on the right of this slide, and also in terms of energy consumption. 1 million ton ethylene producing plant consumes, roughly speaking, 1 gigajoule in energy. 80% of it in the form of combustion of fuel to fire your firebox. And these are the results. What I show here are the results of computational fluid dynamic simulations, accounting for the combustion chemistry, of course, on the firebox side of the furnace. On the bottom, you see there one of the on the bottom placed burners. This bottom placed burner is of course fed by fuel in the middle of the green circle. Primary air is fed at the position of the green circle, and so-called secondary air is fed via the red circles. So you realize that this is a very multi-scale type of modeling exercise, going from the chemistry of the combustion to that of the secondary air inlets to that of the whole firebox. And on the left is shown a snapshot of the flames via the so-called flames, because what is shown there is the temperature field, of course. And the effect of the ratio of primary to secondary air on the temperature field of the gas on one hand on the left side, and then on the right top you see the tube metal temperature, the temperature of the external skin of the coil. And you see that depending on the ratio of primary to secondary air, you have a higher or a lower temperature of this tube skin. And this, of course, affects also the temperature of the inside of the reactor tube. What you see here is on the left a picture of the coke, indeed, which is formed and which, of course, is the result of the high temperature at the inside of the tube. And this coke formation is, of course, very annoying because it leads to an increase in the resistance against heat transfer from the furnace side to the process gas side. It also leads to higher pressure drops, and it can even eventually, via carburization, lead to a breakage of the coils. There is different ways to minimize this coke formation. I will focus on the geometry of the tube at the inside of the coils. You have different possibilities there shown on the right side of the slide. And in the middle of this slide, you see reps which are discontinuous, and that's what I will focus on in what follows. You see here two pieces of rep, which on one hand you see the simulation of the flow field, and then on the right you see simulation of the heat transfer coefficient, here represented by the Nusselt number. You see that there is a drastic effect of the presence of these reps, discontinuous reps, on the heat transfer resistance from gas furnace side to process gas side. This is calculated with CFD, but before trusting that kind of calculations, we want to validate our CFD models. We have done this both related to the simulation of the flow feed and related to the heat transfer. And we have done this in collaboration with the Von Karman Institute for Fluid Dynamics in Brussels. What is shown here on this slide is the result of measurements performed at the Von Karman Institute by means of liquid crystal thermography, which allows you to measure by visual inspection the temperature of the tube skin and infer from there values for the heat transfer coefficient. It's these values of the heat transfer coefficient in the form of a Nusselt number, which is shown on this slide. And this Nusselt number is related, of course, to the Nusselt number corresponding to a bare tube, that is a classical tube without any 3D aspects. And you see that indeed we have a very good correspondence between the experimental Nusselt number field, heat transfer coefficient field on one hand, and the numerical heat transfer coefficient field. These kind of modifications are modifications which consist of adding an obstacle to the inner side of the reactor wall. You could also be inspired by golf and by the dimples. So it's an indentation rather than an obtrusion that you could consider in your wall, and that's what we have done too. And what is shown on the right part of this slide is a comparison in bold between simply ribbed, that's what we have been discussing till now, on one hand, and a dimpled tube on the other hand. And you see that indeed because of the improvement of the heat transfer by the ribs and by the dimples, you have, compared to a bare tube, a decrease of 53 for the ribs and of 45 degrees Kelvin for the dimples of the inside tube temperature. So that's the good news. And of course, the good news is the corresponding decrease in the rate of coke formation. 50% for the ribs and 39% for the dimples. If you would only look at these figures, you would go for the ribs. But when you look at the pressure drop differences between the bare tube on one hand and the ribs and the dimples on the other hand, you see that you have a penalty for the ribs, which is much more pronounced than the penalty for the dimples. And that's why we advocate and we have patented together with BASF the idea of dimples in the tubes. And these dimples are shown again on the left of this slide. And we have been playing with of course, the configuration of the dimples with respect to each other on one hand. But not only that, we have also been playing with the shape of the dimples. On the bottom left are shown different possible shapes, and via a mathematical description of this shape by using so-called Bézier curves and using a Dakota available software, which is based on an optimization of an objective function via a genetic algorithm, we have come to a hard shape as an optimal shape for the performance of the reactor coils during steam cracking. There again, of course, we have been, during this optimization, we have been confronted with a Pareto front. That is, the good news of the effect of the dimples is that the Nusselt number is increasing. The bad news is that the pressure drop is increasing compared to a bare tube, and you cannot increase the Nusselt number at one point without also increasing the pressure drop. And that's the so-called Pareto front, which corresponds to the red lines in this slide. And the color code actually corresponds to the generation number. We have been optimizing the shape of the dimples, starting from spheres and ending up by a heart over more than 1,000 generations of values for the Bézier curve parameters. And then finally, we have been simulating an industrial millisecond propane cracker for the production of ethylene, propylene in particular here, of course. And you see that indeed, when you look at the temperature field on one hand, and on the right side, the rate of coke formation, that there is clearly an effect of these hard shapes on the corresponding fields. When you do the calculation of the savings because of these heart-shaped dimples compared to bare tube, we arrive at a 4% CO2 emission reduction for such a millisecond propane cracker. For a very mature technology like steam cracking, that's a lot. But when you put that into the perspective of the climate change, and some people call it climate crisis, and into the perspective of the targets set by the European Commission, for example, and for example, the Fit for 55 plans of the Commission, this is not way beyond what we really need for in terms of CO2 reduction. And of course, dimples is one thing, and I'm sure that by implementing other changes to the existing steam cracker process, you can for sure, on a time scale of let's say 5 to 10 years, reach a 20% reduction of the CO2 per ton of ethylene produced. But the question is, can you go beyond with this type of technology? And is there an alternative future for steam cracking? Could it be the electrification of steam cracking? We have, at the very beginning of my talk, I've been mentioning Cheula heating, resistive heating, as for example, published in the paper, science paper of people from Halder Topsoe and the group of the D.Yu Technical University of Denmark, of Korkendorf. But there is, of course, also and applied to steam reforming in that case. But you could also apply this to steam cracking. One could think of doing that. There is inductive heating. There is microwave heating. And a basic difference between this microwave heating and eventually even depends how you implement it, inductive heating, is that in contrast to the heat transfer mechanism we have been discussing till now for steam cracking, microwave heating is a bulk phenomena. It does not require transfer via an interface. Okay? And it is indeed this interfacial heat transfer which indeed was causing this Pareto front, this dilemma which consisted of saying that you could not improve the heat transfer without getting more pressure through. With microwave heating, where you don't need interfacial transfer of energy, of heat, you do not have this dilemma. And the same holds for, and this is also an electric type of technique, is the so-called rotodynamic reactor technique, advocated by the company Coolbrook, which is an artist impression of which is shown on this slide. It's starting from electric power, which is rotating a shaft, and on the shaft is fixed a so-called rotor in the middle of three cascades of vanes. The first one is a static one, the third one is also a static one, and the middle one is the rotor one. And by the dimensions and the geometry of the static vanes and of the rotating vanes, the gas which is entering the reactor and transformed from inlet to outlet port via a vaneless space is heated up on a very short time scale by converting the kinetic energy that the gas gets via the rotor, not in contrast to what's happening in a compressor, not into pressure, but into heat. Coolbrook is indeed claiming that on a time scale of 10 milliseconds, the temperatures needed for steam cracking can be reached via a mechanism that does not require interfacial heat transfer, by bulk heating of the gas phase, by having kinetic energy of the gas phase converted into heat via dissipation of this kinetic energy. This brings me to the conclusions and perspectives of my talk, and there will be very high level type of conclusions. I hope I've convinced you that by combining theory and experiment, we really can come up with the design of new catalysts, new processes, which we will really need indeed if you want to tackle the challenge of our period. If you want to put a timeline on the solution to these challenges, well, it is on the bottom of this slide here, and it will consist of a transition from hot flames to green electrons on one hand, and it will consist of substituting fossil raw materials by renewable sources of energy and of materials, including in a transition period also methane. We are all of us are working on this, but I want to mention in particular Synergy, which is a consortium of companies and academic groups working today, this very moment, to apply for a so-called coordination and support action with a deadline at the end of this month to indeed contribute as a community to this type of scenario. At the very end, of course, I want to acknowledge all the people that have been helping to come to all the results I've been showing, the LCT faculty and visitors, for sure. The people working at the spin-off company I briefly mentioned, postdocs at the Laboratory for Chemical Technology, and of course I want to take the opportunity to also mention a book that I have been co-authoring with Gregory Yablonsky, you all know, and Denis Constales, a mathematician we are closely collaborating with. Having said that, I want to thank you for your kind attention.
Thank you very much, Guy. That was really a pleasure to listen to you. So a round of applause, even if we cannot probably hear this applause from the audience. I think it was an excellent example of the top-level chemical reaction and reactor engineering, and very much in line with the spirit of the work which was done by Professor Slin'ko. So experiments, theory, and then design. So we are really grateful for this lecture. Do you want to add, Tapio, something?
Thank you very much, Guy. You nicely illustrated how to go beyond the classical reaction engineering on one hand to DFT calculations, then to CFD and to process intensification. In one sense, we can be happy that we go from linear economy to circular economy, because that puts not only new challenges, but for new opportunities to our science, which I think is flourishing nowadays, because not only the theoretical inventions, but the practical needs and the societal demand is so great. Thank you very much, Guy.
Thank you.
And then we can move probably to the second plenary lecture. Can we get the slides? Who is now taking care of the slides? Professor Zagoryka hopefully can help us.
Maybe, Guy, possibly you have to stop your presentations. There is some in the upper part of the screen. Yeah.
We'll give it a try, but I think the most easy thing is that I leave you.
That's also an option.
That's the most drastic option I will take.
Well, possibly it's resolved, huh?
Okay, one moment.
In the upper part of the screen. Possibly.
But we need to go to the next presenter anyway.
Yes, just a minute. I will contact Tatiana.
30 years plus experience in the field of chemistry, refinery, oil and gas and energy industrial sectors. He graduated from industrial chemistry in Venice, and then started his industrial career in '91 with ENI Corporate Research and Development. He has observed several projects in Africa related to LNG, floating LNG, gas to liquids, Fischer-Tropsch, methanol, gas to power, ammonia, etc. And today we will hear the plenary lecture devoted to process technology for energy transition. And that will be about production of hydrogen and CO2 capture, storage, and utilization. Dr. Zenaro, the floor is yours, please.
Good afternoon, ladies and gentlemen, and thank you, Mr. Chairman, for your kind introduction. And a special thanks to the conference organizing committee. It is really an honor for me to have been invited to this prestigious event. First, to start, I would like to know if you see my screen.
Yes, it's perfect now. Yeah, we can see. Please go ahead.
That's fine. That's fine. So let me start in. Along this lecture, I would like to give you an overview on the use of hydrogen as a key driver for the energy transition towards the replacement of the fossil energy fuel. Quite a tough argument in this period. At this scope, I will briefly describe the result of the most recent scenarios with a focus on the European strategy for the green and blue hydrogen. And then we will see the status of the low carbon and green hydrogen production technologies and the technological trends for its storage and delivery. I will then close my presentation with an overview of some of the activities that my company, an energy company, ENI, is carrying out projects and technologies necessary to the achievement of the challenging decarbonization targets that ENI and we all have in 2050. So the first world production picture, as usual, concerning the pure hydrogen, according to IEA and the Rystad Energy, in 2019 there were about 75 million tons, almost entirely used as a chemical raw material for industrial uses, and only a marginal share was used as an energy source for the so-called hard-to-abate industrial sector. Another 45 million tons that are not included in this figure here was the hydrogen produced as syngas component for specific application, like, for instance, methanol synthesis. The hydrogen production, as you see, is entirely supplied today by fossil fuel, natural gas, with around 6% of the world natural gas consumption, and coal with about 2% of the world consumption. And this is the cause of about 830 million tons per year of CO2 emission. First of all, I would like just to share very briefly what has become the new hydrogen color code, which indeed, as we all know, is a colorless gas. Obviously, the need was dictated by the ease of identifying with a simple color a specific hydrogen production chain. And this certainly helps the communication, especially in non-technical sectors. During the presentation, we will see essentially the blue-green hydrogen passing through to the turquoise hydrogen, which means the methane pyrolysis system, just as one of the new way considered. Going back for the hydrogen expansion figure, in the last year, the analysts produce dozens of scenarios with different ranks based on the different global warming degree limit considered. The top right graph, there is an elaboration, an internal, an ENI elaboration, which sum up the 2050 global projection of the hydrogen share in the energy consumption coming from the main agency and the consulting group. There are, in all these analyses, 3 scenarios. The base reference scenario, the 2 degree C scenario, and the most challenging 1.5 scenario. And let me see if I can activate sorry, yeah. Okay. Okay. So, as you see, the largest difference or uncertainty, if you like, is in the final projection at 250, especially for the most challenging scenario. The gap is 6 to 17% of energy or hydrogen share in the gross energy consumption. According to the IEA net zero emission scenario, very famous in this period, the global hydrogen use will expand more or less to 80 million tons in 2020 to more than 200 million tons in 2030. So in 10 years, there is a step increase. It is interesting also to observe that the percent of low carbon and green hydrogen versus the green hydrogen is increasing considerably from 10% in 2020, 7% in 2030, up to 98% in 2050, and with gray hydrogen production almost absent, almost disappear. Now let's have a look at the situation in Europe. For the recent Fit for 55 update package that the EU Green Deal applied, which increases at minus 55% the emission reduction in 2030, has accelerated the national and European policymakers to develop the decarbonization framework. It is well known that the hydrogen is an integral part for the European Green Deal strategy to reach the carbon neutrality. The so-called EU hydrogen strategy is more specifically based on a phased low carbon hydrogen penetration plan. As you see, it's phased in 3 main, let's say, periods. By 2024, with the installation of at least 6 gigawatts of water electrolysis to produce 1 million tons of renewable hydrogen. By 2030, 40 gigawatts of renewable hydrogen electrolysis are foreseen to reach in 2050 all hard-to-abate sector with something like 500 gigawatts of electrolysis capacity and the diffusion of the renewable hydrogen technology on a large scale. This plan, as you see, is supported in 25 years by a sustainable financial mechanism for several billion euros, especially for the green hydrogen. And the European Clean Hydrogen Alliance, which is a collaboration between public authorities, industry, and civil society, has the task of developing an investment agenda and a pipeline of concrete projects. ENI has recently joined the Hydrogen Europe Association and also the European Clean Hydrogen Alliance, and was one of the 17 partners from the energy sector who funded the Hydrogen for Europe study that is available on the website. This study was prepared for the sole scope of assessing the contribution of low carbon and renewable hydrogen to the European energy transition. And they consider two interesting scenarios or pathways. The technology diversification pathway that is based on first already approved national targets and very important, no obstacles to the development of different technologies, especially the low carbon technologies, the blue hydrogen, just to be more precise, and a perfect match between the market request and the investment decision to be taken. Different, the renewable push pathway prioritize the deployment of the renewable energy technology, wind, solar, water split, through the increase of targets on the share of renewable in the gross final energy consumption that probably are also beyond the current policy goal. The main messages from this study was Europe is the area with the highest hydrogen growth prospect to the respect of a global situation, which consider more than 20% of share of hydrogen in the final energy consumption in 2050. The hydrogen produced from renewable energy source has the highest priority, but the low carbon hydrogen production is not excluded, like blue hydrogen, and in the scenario appears also the methane pyrolysis, and hydrogen based or not 100% renewable electricity, which, if you recall, the color code is the purple and the yellow hydrogen. All these form of low carbon hydrogen, according to the study, are needed in the short, medium terms to reduce emission first from the existing hydrocarbon production and complement the renewable hydrogen until a sufficient green capacity is available to cover the future demand. Just a couple of information captured from the study. The very different assumption of the two scenario highlight the different hydrogen penetration rates. In the renewable push scenario, the green hydrogen in 20 years, in 2040, become the largest source of hydrogen with a step increase up to 72% in 2050, which could raise at 81% if we consider also, according to the scenario, the imported green hydrogen. While in the technology diversification, a more homogeneous or balanced growth of the renewable energy is shown, with let's say arriving in 2050 with a more or less, if you see, 50-50 balance from green hydrogen and the blue hydrogen. As shown in the bottom right graph, the two pathways bring to a very different cumulative investment estimate. It is an estimate which includes all the life chain of the technology applied in this scenario. And you see that especially the renewable push pathway arrive in 2050 with an impressive cumulative investment of around 3 trillion, mostly linked to 1,600 gigawatts of installed capacity for electrolyzer. Also, offshore electrolyzer, offshore wind is included in this figure. Going ahead, let's now move into the status of the hydrogen production, transport, and storage technologies in this new energy transition context. The traditional hydrogen production routes are mainly based on thermochemical conversion with the catalytic reforming, partial oxidation processes, or gasification processes. The downstream presence of a CO2 capture and sequestration process make the difference in the final product valorization, of course, as in the case of the blue hydrogen production. Thermochemical process also include methane pyrolysis or methane cracking. That is an endothermic process that produces solid carbon and gaseous hydrogen and hydrogen. The technological maturity of this technology covers all stages between an advanced R&D activity for the new, especially plasma application, to commercial application. Indeed, the latter relates to plant address more to solid carbon production instead of hydrogen. For the green hydrogen, there is no story. The electrolysis technology with electricity coming from the carbonized system, nuclear or renewable source, are the one to consider. Moving ahead, just a focus in the new, considering the new paradigm dictated by the energy system transition. The hydrogen production by natural gas reforming is the process mostly considered today. With a renewed interest from licensor as well as scientific community in studying new ways to increase the plant efficiency, especially when they are integrated with carbon capture plant. We just heard about the possibility to consider as the electrification of steam cracking. This is for sure an area of interest. The standard technology for the steam methane reforming that is widely used to produce high purity hydrogen in the refinery. The feedstock range from natural gas, of gas from refining processes, LPG, and also in some cases liquid fuels like naphtha or kerosene. The typical fire tubular reformer is based on a radiation section with specific catalytic tube with different geometry depending on the technology provider, and a burner arrangement. And a second aside convective section for the important part of the heat recovery. Methane steam reforming is an endothermic reaction catalyzed by nickel-supported catalyst at relatively high temperature and low pressure. A typical feedstock flexible hydrogen plant include also a pre-reformer unit, a downstream water gas shift unit, and a PSA, a pressure swing absorption package for purifying, for producing pure hydrogen. Concerning the other technology, the autothermal reforming, this is a dominant technology when syngas rather than pure hydrogen is the desired product, especially at large capacity or for low production of low hydrogen CO ratio, like for use in the methanol reaction or Fischer-Tropsch reaction. The ATR reactor consists of a burner that is a key element to provide the mixing of the feed streams in a turbulent diffusion flame regime. The combustion chamber, it follows the fixed catalyst bed section, the reactor lining, and the pressure shell as reported in the picture. This reaction is a combination of thermal partial oxidation with oxygen and steam reforming. The heat released in the gas phase oxidation at substoichiometric ratio is used for the endothermic reforming stage, catalytic reforming stage based on catalyst based on nickel, also in this case, and there is in principle no need to external heat supply. This is a very important point, especially in view of the final CO2 emission figure of this system. Oxygen is produced from air, and so it is required an air separation unit, and the specific electric energy required is about 500 kilowatt-hour per tons of oxygen. Also in this case, to arrive at an hydrogen production, it is necessary first a pre-reformer unit for flexibility on the feedstock, and a downstream water gas shift and PSA package. In the following slide, I wanted to put the attention when this system, SMR and ATR, are combined with a carbon capture plant in terms of CO2 emitted, and also the possibility to capture at a high rate the CO2. For the SMR, as you see in the three figures here, there are at least two options to capture the CO2. In one case, the capture system is upstream the PSA unit with two possible configuration. One in recycling back the style gas from PSA to the SMR furnace, and a second one which is recycling back to the SMR burner system, also raw hydrogen from the water gas shift unit. This has an impact in the final CO2 emission figure of the system, as well as in the maximum CO2 capture rate. The third figure in the bottom is considering a second option in which the carbon capture plant is placed just outlet, is placed in the flue gas stream from the steam methane reforming furnace. It's a typical post combustion case. As you can see in the bar chart, as a result of these different configurations, in this case we consider the IEE JNG technical report, and we analyze it in introducing some emission factor very important for the LCA analysis. As you can see, I was saying there are a significant difference from option to option. In the most favorable case, we reach 90% capture, CO2 capture, overall CO2 capture, and a fairly low 2.2 kilograms of CO2 equivalent per kilogram of produced hydrogen. That, in comparing with an SMR plant without capture, the figure is quite different. The two options highlighted here, the 1 and 2, is giving to a different capture rate, I would say considerable. Of course, the use of hydrogen is reducing the emission at the furnace side. Let me give you a few elements in the comparison from SMR and ATR, both cases enhanced with the capture system, and you see that you see it is almost know that the SMR is a net steam and heat importer and appears more emissive than ATR, while the ATR is the largest electricity user, due of course to the air separation units present. From a specific CO2 equivalent emission point of view, the comparison in any case could arrive at the same result if we basically maximize the steam recovery and the thermal integration in the SMR plus capture case. Basically, the HP steam produced by a steam methane reforming can be used as driving fluid in a steam turbine to produce electricity power and low pressure steam for the carbon capture plant. We are considering a standard amine unit in the regeneration column. In the case of ATR, the use of an electricity mix from the grid with a relatively low emission factor, and in this case we use the average value in 2019 in Europe that accounts for something about 24% of renewable source. You see that the result could be comparable. This is an interesting aspect that we have to consider in the selection of the technology. Another element important here is the importance in the quality, especially for the SMR, in the quality of the imported natural gas used as a process feedstock and fuel gas. In fact, the emission factor of the imported natural gas might greatly impact the indirect GNJ emission of the system and of course the overall CO2 equivalent specific emission. The graph here show the impact on the overall CO2 emission by increasing the natural gas emission factor, the impact factor. For different solution, the CCS enhanced steam methane reforming with an imported steam with auto production of steam, and 2 ATR enhanced with capture at different electricity impact factor, a different content of renewable energy source. The graph report also, this is very important, the taxonomy threshold set by the European Community at 3 kilograms CO2 equivalent per kilogram of oxygen, which puts the blue hydrogen only marginally taxonomy aligned. Basically, projects based on blue hydrogen production are eligible to the sustainable financial package by the European Community Commission only when natural gas has a low GNG emission factor. This is a key point, and the electricity comes from a mix of high renewable content. Let's have a brief look at the water electrolysis technology perspective. The technology, as well known, are 3 at different maturity. The alkaline electrolysis that is well mature, commercial technology since 1926. Hydrogen ions are transported in the 2 electrodes operating in a liquid alkaline electrolyte solution and separated by a diaphragm of composite material. The proton exchange membrane electrolysis that was first introduced in the 60s by the General Electric to overcome some problem of the alkaline electrolysis. And finally, the least developed electrolysis technology, the solid oxide electrolytic cell, the SOEC. They have not yet been commercialized, although individually companies are now aiming to bring them into the market. Some of the water electrolysis characteristics are very important in the future application perspective. I simply recall you the European hydrogen strategy target of 40 gigawatts in 2030 and 500 gigawatts in 2050 for the green hydrogen production. And the graphs here reported that are an elaboration of the IEA analysis clearly show the step increase in efficiency in the stacks lifetime, the stacks module lifetime, and the CapEx decrease in the next 30 years. The main reason for such technology cost reduction is mainly ascribed to the technology innovation, of course. For instance, in the field of the material, the material for the electrodes and the membrane, the presence or not of novel metal, and very important, the industrial learning by doing evolution, especially for the SOEC system, and the economies of scale in the manufacturing of the processes. From a production cost perspective, the levelized cost of blue hydrogen, these are data recently presented in August by BIS, are fairly constant, as you see, and flattening in the range of 2.7, 3.1 kilograms euro per kilograms of hydrogen. While for the electrolyzer system, besides the electricity cost, the grid electricity cost, which dominate the production cost, it could be appreciated again, especially for the SOEC system, the trend in CapEx decrease over time, and the incidence of the variable cost associated to the periodic replacement of the stacks module. Okay. Let's move now in a brief, let's say, view of the hydrogen storage and delivery technological status. The hydrogen, like all gases, can be stored and transported, and there is a considerable experience that dates back the beginning since last century. Nevertheless, such experience is limited to a small to mid-sized industry. Today, the growing green hydrogen scenario needs a sustainable scalability of hydrogen storage and delivery at very large capacity, as we have seen from the European and not only projection. The application of hydrogen storage can be divided in two main groups: the stationary storage, the on-site storage at the point of use, or the on-site storage at the point of production. And this, as we will see, is linked to the concept of the hydrogen valley, and the mobile storage, or if you prefer, the storage for mobility. Due to the, let's say, due to the hydrogen low volume energy density compared to the fossil fuel, physical and material-based transformation are required to limit volume, weight of the containment system, and of course reduce the relevant cost. Concerning storage and delivery technology, of course, they have a very different volumetric and gravimetric different ranges, resulting, as it is reported in the table, a different applicability of the storage volume or distance of transport. And in this case, the physical base transformation like compression and liquid hydrogen are of course state-of-art technology with a TRL 8 or better 9 fully industrialized technology. On the other side, the material-based transformation, that is a very interesting area for the material science, are less mature. I'm speaking about the molecular organic framework, the carbon system, the hydrate, and they have a relatively low readiness level. We will see something about that in a while. So among the physical-based transformation, compressed hydrogen and cryogenic liquid storage and transportation do not need too many descriptions. Compressed hydrogen transport is today carried out both via trucks, train at a pressure up to 300 bar. It is worth to mention that from a containment system point of view, it is growing the use of composite pressure vessel of type 3, the one based on a carbon fiber wrapped on an internal thin liner of steel or aluminum. New routes in the area of physical transformation are the high pressure cylinder designed to work at 950 bar at room temperature. These systems are classified as type 4 pressure vessel, and they are based on carbon fiber wrapped on a internal liner of high density polyethylene. As a result, these cylinders are lighter and more resistant to hydrogen embrittlement than the type 3 cylinder, the one with the metallic liner. In the picture, you see an example of these cylinders arranged in an isomodal rack. A curiosity is the first example of hydrogen transport by means of a cryogenic carrier, similar to the LNG shipping industry, is the HESC project, the Hydrogen Energy Supply Chain, led by Kawasaki. The project, the aim of the project is to demonstrate the transport, the liquefied hydrogen transport on a distance of 9,000 kilometers from Japan to Australia. This is the picture of the first liquefied hydrogen carrier launched in December 2019. Okay, the liquid organic carrier is another interesting example of material transformation. In this case, it's chemical transformation. It is moving into the final demonstration step before its commercialization. The storage and transport concept is typically based on a reversible catalytic hydrogenation and dehydrogenation reaction with different chemical couples of organic compound, like, for instance, the one used by the Japanese company Cheula, that is toluene and methylcyclohexane. Cheula announced last year the Spera hydrogen project with the intent to demonstrate the entire transport chain concept to connect the city of Spark in Brunei with the Kawasaki city in Japan. Ammonia is another attractive hydrogen storage medium for several reasons, as you see highlighted also in this slide. Of course, the very high volumetric density, the very mature synthesis, handling, and transportation, and the fact that the ammonia plant could in principle be easily retrofitted to the use of hydrogen from electrolysis. There is also a possible ammonia use as a carbon-free fuel in internal combustion engine and gas turbine. The last and probably the most interesting concept of hydrogen material transformation, as I introduced before, is the storage by absorption. It is very attractive because it has the potential to lower the overall system pressure for an equivalent amount of hydrogen, yielding safer and operating conditions. This is extremely important, and the advantages of this methodology are that the volumetric and cryogenic constraints are basically abandoned. Of course, the mobility sector is paying large attention to the development of this area. As already introduced, the hydrogen carbon material has a relatively low technology readiness level, and are still ongoing several validation, R&D validation programs. The US DOE is periodically setting the KPI target as the material performance increases. The storage material can be classified in nanoporous material and hydride, which respectively capture hydrogen by physisorption and chemisorption process. Nanoporous material like the metal organic framework, the carbon nanotubes have the advantage of an absorption process completely reversible and a fast kinetics. This is in contrast to some hydrogen absorption by several metal and metal hydrides and complex hydrides that are somehow reported in the figure here, where it is also indicated what are today the minimum requirements established by the DOE in terms of gravimetric storage density, the blue dotted line, and the blue dotted line, and the volumetric capacity of the system. Very important element for the vehicle mobility sector. In the last part of my presentation, I am pleased to introduce you an overview of the ENI activity with a focus on the decarbonization project and our proprietary technology. Just to give you an example of how the energy company are today moving in this challenging period, especially in perspective of the target that we have. With few, let's say, light detail, I don't want to bother you with this organizational change, but in June last year, and he launched a new organization business with two new business groups, functional to the new strategic objective that it is reported in the right-hand side of this slide. The natural resource, which focuses on the sustainable valorization of the upstream oil and gas portfolio, the wholesale gas marketing, and projects related to forest conservation and CCUS, and the energy evolution, dealing with the evolution of the energy generation systems, business, and power and refinery and chemistry as well, and the transformation and sale of products from fossil to bio, blue, and green. There is also a central structure, the new technology R&D and digital unit, which has a strategic relevance to ENI as let's say research and development and technological innovation are considered key drivers for creating value and growth. Concerning the new energy strategy, as you see, this was defined early this year. It relaunched the short and medium and long-term operational objectives that, as you can see, are quite challenging. It will lead to a carbon neutrality in 2050, including all GHG scope 1, 2, and 3 emissions. Among the levers to target this objective, the net zero emission, there is also the blue hydrogen and green hydrogen that was central to my presentation. ENI is evaluating a number of initiatives in Middle East, North Africa, Asia and Pacific involving blue and green hydrogen production, as well as also blue and green ammonia. But let's say in Europe, as you can see in this slide, in this snapshot, there is the concentration of the ENI initiative. I would like to jump in one of the most important, since ENI has identified in the Ravenna area the opportunity to exploit the combination of the depleted offshore gas field with the infrastructure still in the operation, still in operation. The first demo project in Ravenna is announced for 2023, and it will allow us to gain competencies on the entire CCS value chain. This process, which is based on safe and validated technologies, represents the fastest way to effectively reduce CO2 emissions without upsetting existing industrial processes. Ravenna Hub, with an estimated storage capacity of 500 million tons, could give a significant contribution to the containment of the climate changing gas emission in Italy. For instance, by capturing third-party industrial CO2 emissions, especially from the hard-to-abate sector, reducing CO2 emission from the existing ENI plants, producing blue hydrogen to be used as feedstock for biofuel production, also in our biorefinery, to decarbonize hard-to-abate sector, as said, and for heavy-duty transport, shipping, and aviation. Also, the production of blue power for decarbonized electric production is intrinsic in this development scheme, as well as also the fact that blue hydrogen and CCS will contribute to the development of the concept of the hydrogen valley, which is extremely interesting one. Very rapidly, in the ENI strategy, of course, there is the renewable electricity. So we decided to start a collaboration with Enel by sharing our competencies and experience. And we launched 2 pilot projects to produce green hydrogen through electrolyzer powered by renewable energy. The electrolyzer will be located near 2 of the ENI sites in Cheula, the biorefinery in Cheula, and the Taranto refinery. Each of the 2 projects will feature an electrolyzer of around 10 to 20 megawatts and are expected to start generating green hydrogen by 2023. Both initiatives have been proposed also as important project of community European interest, the IPCEI project, with the objective to study the best configuration, to evaluate technically and economically feasibility, the operational continuity, especially in the interconnection with the site, and to define the necessary regulatory framework. Another initiative is the hydrogen for mobility. Very briefly, we have considered, we have signed 2 agreements with Toyota, one in San Donato Gianesi, Milan. Toyota is the provider of the Mirai fuel cell car, for the production and to realize a selling point, what we will call in the future ENI mobility point, producing by means of an electrolyzer in the selling point 700 bar of hydrogen supplied to the car. In Venice, different, it will be installed a service station with 10 cars and 3 buses, and the hydrogen in this case will be transported to the station on a tank distribution at different pressure, depending on the bus or the car utilization. To conclude my lecture, I would like to present 3 ENI proprietary technology that will play for sure a role in our decarbonization path. One is called key gas, is basically a short contact time catalytic partial oxidation. The technology is characterized by feedstock and oxidant flexibility, and it limits the use of some highly energy intensive steps typical of the traditional processes. The proprietary reactor and noble metal catalyst, which are integrated into four main sections as identified in the picture here, could reduce the reaction volume 1 to 2 orders of magnitude compared to the current steam methane reforming or box technology, giving to this technology also interesting application at a small scale. The key gas technology validation is progressing, and the first demonstration plan is under advanced construction inside the ENI refinery of Taranto, with a nominal capacity for syngas production of 8,000 normal cubic meter per hour, or 5,000 normal cubic meter per hour of hydrogen. In parallel, there are extensive engineering studies, as I said, for the application, for instance, in the methanol production or the conversion of biogas in small scale application. Second technology I wanted just to briefly introduce is the ESWIT, that is the ENI proprietary carbon capture technology. ESWIT fluid technology is based on a mixed solvent absorption system, which combine the ionic liquids like D.Yu, that is an amidine organic compound, mixed with alcohol and, when necessary, a selected physical solvent. This formulation enables not only CO2 capture, but also H2S and mercaptans capture from natural gas and flue gas, with some, let's say, advantages that are here reported once for all: the ionic liquid regeneration, lower duty. The third and last proprietary technology I wanted to show you in the next minutes is the carbon capture mineralization. It is interesting because it's one of the rare example of a carbon utilization project. In fact, this is based on the reaction between the carbon dioxide and the olivine, a very common magnesium iron silicate, widely available in high purity outcrops. And the reaction is well known, is exothermic, thermodynamically favorable, but with a very slow kinetics occurring on geological time scale. Eni has filed a patent on a new carbon capture mineralization process to deploy the reaction at the industrial scale. With dedicated experiment program was carried out especially on the reactor technology selection to maximize the gas liquid mass transfer. The process is very attractive with a high nominal uptake of CO2 up to 0.45 tons of CO2 per tons of minerals, and forming, let's say, non-toxic phases that can be directly used in cement formulation. This is, in fact, the application we are considering. I think that this technology, there is a study in progress for this technology, and just to conclude, we would like to apply this technology together with the ISWIT technology in the Ravenna CCS Hub project, as you have seen, as this is the ideal context that can be considered for the demonstration of this technology. I thank you for your attention, and hope that I have given to you some, let's say, messages to be used in the scientific community for the next technology improvement and innovation.
Grazie mille, Dr. Zenara. So we are very grateful for your lecture, also addressing the industrial side of say the processes what we're dealing, or many people here in the audience are dealing from the academic perspective. And we're also grateful for sharing recent projects and what you have at ENI. Some of them, they would look fantastic even a few years ago, including utilization of ionic liquids for CO2 capture, which was considered to be too expensive. So we are really looking forward, and we'll closely monitor what is the progress of this and the other process what you have mentioned. According to the program, once again, thank you very much. According to the program, we should have a short break for 15 minutes, and we will do that. And after that, I strongly ask all the participants to come back after stretching your legs and drinking coffee, because we have two more exciting presentations, two more keynote lectures. Thank you very much. And with that, I would like to conclude this particular session. Okay.
I think we can start the session.
Hello together. Hello.
Hello.
Can you see my screen and presentation?
Yes.
Okay, wonderful.
So we good afternoon, good morning, good night, depending on where you are. And welcome to the first keynote lecture session of the conference. My name is Luis Gandia. I'm professor of chemical engineering at the Public University of Navarre, Spain. And I would like to acknowledge the organizing committee for inviting me to chair this session. This is a big pleasure for me. Our first speaker is Professor Dr. Ingenieur Hans-Jörg Freund from the Technische Universität Dortmund, Germany. Professor Freund was head of the group Catalytic Reactors and Process Technology at the Alexander University of Erlangen-Nuremberg by nearly 10 years. And since the beginning of this month, he has taken over the position of chair of the Institute of Reaction Engineering and Catalysis at the Technische Universität Dortmund. His research activity covers such as scientific areas such as model design and optimal chemical reactors, process, additive manufacturing of cellular structures as novel catalyst supports, and reaction kinetics. The focus of Professor Freund's research is on the development of energy and resource-efficient chemical processes, with a special focus on the model-based design of catalytic reactors. In a comprehensive approach, innovative process, reactor, and material concepts are considered, which includes the evaluation of different process intensification options. In 2019, Professor Freund led the XXIV International Conference on Mixed-Structure Reactors and Catalysts at Germany, and he's author of more than 300 scientific contributions to prestigious journals and conferences. Well, the title of this lecture is Additive Manufacturing of Tailor-Made Catalytic Reactors with Optimal and Flexible Transport Properties. So, please, Hans-Jörg, the floor is yours.
Thank you very much, Luis, for the kind words, the kind introduction. And also, of course, thank you to the organizers for inviting me to give this keynote presentation. Although it's not in presence at Milan, I would have loved to be there actually, but all of us, I guess. So we will do our best and see what we can do together here at this meeting. So it's actually, as mentioned, my first presentation in my new position as chair of the Institute of Reaction Engineering and Catalysis at TU Dortmund University. However, the results I'm presenting obviously are from the last couple of years we have achieved together with my group at the University of Erlangen, Nuremberg. However, actually, I have moved with more or less my whole research group to TU Dortmund, so you can expect more follow-up work also in the directions I will show you today. And the topic is additive manufacturing of tailor-made catalytic reactors that are optimal, but also we try to design reactors that are flexible, and these I will try to show you in my presentation. At first, I will give you a brief overview of our research areas. So everything is about reactors. So that's why it's a perfect conference actually for us. And we try always to achieve an optimal reactor by rigorously optimizing the balance equations. So optimization problem using balance equations and kinetic expressions. And then we try to answer the question, what would be the best optimal reactor? And in order to do this, you need obviously reaction kinetics. So this is another research line. So we do reaction kinetic experiments as well as modeling, both in smaller lab scale and also in, I would say, meter scale, more industrial application reactors. And once you have done all this, you have this optimal result, then the question is how to realize this actually. So how can we now match the optimal transport processes with the reaction conditions we would like to achieve? And here, additive manufacturing of catalyst support structures comes into play. This is this circle here, and this is the talk I will give today about this novel catalyst support structures that we can design and we can fabricate by additive manufacturing. If you now compare, let's start from the basics. If you now, let's say, look at the options we have, let's say, the two established technologies. We have the randomly packed fixed bed reactor on the one side. The main advantage is here that it's an easy design and it's a simple manufacturing of the cat pellets, and you have a high catalyst inventory. However, with regard to the transport processes, this design is not so favorable because you have a high pressure drop and you have a limited heat transport in radial direction. Also, your design flexibility is quite limited. On the other hand, we have these monolithic honeycomb reactors that are also well established, particularly where you have high flow rates because the pressure drop is low. So it has some really favorable properties. But also here, the design flexibility is quite limited, and also you don't have, let's say, an interconnection between these channels. And that's why we came up in Erlangen. And if I say we, I mean my colleague Wilhelm Schwieger and myself. We have done a lot of work in these periodic open cellular structures, short POCs, where we try to combine the advantages from both worlds, basically. And these POCs are basically a unit cell. Here in this picture, it's a cubic unit cell that is reproduced in all spatial directions. And then you have a 3D network of struts interconnected to solid matrix. And also you have a channel system that is also communicating. So you will have a radial mixing, and this enhances, of course, also the radial mass transport. The nice thing is that the morphology, if you do this by 3D printing, it's a very well-defined morphology. So you can systematically analyze, for example, the size of the pores here. You can analyze the influence of the size of the strut, thickness of the struts, and so on. And once you have understood this, you can also try to optimize these structures. You can then play around with the different geometrical properties and try to match the transport processes you want to achieve. We have done this in the last now more than 10 years. I'm always a bit joking and say we did 3D printing before it was fancy. Yeah? And nowadays it's a bit a hype, but we started the work the first publication was in 2011, and we started to analyze the pressure drop in a single phase flow, and then eventually we added on complexity to the system, and we have also done some nice collaborations with a group of Enrico Tronconi in Milan. So we have done a lot of work in this direction on pressure drop, also on multi-phase operation, on pure heat conduction in the solid matrix, but also on the overall heat transfer. And the overall heat transfer is the first storyline I want to highlight a bit here. And I want to give you a glimpse on why this is interesting to do. So what you see here in this figure on the right-hand side is you see 3 times more or less the same geometrical structure that has been manufactured by selective electron beam melting. This means basically you have a metal powder and then you do 3D printing of this metal substrate, and then you get this kind of structure. And then of course always the question is how to bring the structure into the reactor tube, and then you can have different possibilities. You can just fit it loosely in this tube, or you can wrap an aluminum foil around this in order to enhance the wall contact. Or, and this is now the nice thing with 3D printing, you can directly print the wall attached to the structure. Yeah, so basically by printing, you do it layer by layer, and around the structure, you can directly print the solid wall. And now we want to investigate how the wall contacting now has an influence on the overall heat transfer performance. And if you compare now the overall heat transfer, plotted here on the left over the mass flux here, then the color code, by the way, is the same as here. So the green one is the loosely fitted. And if you now look at a certain mass flux, you see that the overall heat transfer increases considerably if you enhance the wall contact, either by an aluminum foil or by direct contact, namely by printing the wall attached to the structure. So this is one, I think, of the key issues. Also, the same applies to open cellular foams of irregular morphology. The wall contacting is a key issue here. And in 3D printing, you can address this issue by certain measures. In this slide, I have tried to combine, let's say, all the results we have achieved in a study by Corinna Busse. She was a PhD student, jointly supervised by Wilhelm Schwieger and myself. And the plot here, the most interesting in this plot is the color code. I will try to explain this. The color code refers to the difference of the overall heat transfer from the POX system minus fixed bed. This means when this delta is greater than 0, then the POX have a better overall heat transfer. And if it's smaller than 0, then the traditional particle-packed fixed bed performs better. And this black line here is a separatrix line in this diagram. And on this diagram, we have as an additional parameter here, we have on the y-axis the solid matrix conductivity of the bulk material. And we have the superficial mass velocity. And what you see here is that, let's say, for a given solid matrix conductivity, there is a certain superficial velocity, which is exactly the separating point. If you go above that velocity, then the conventional fixed bed is better. And if you go below, then the POX system is better. This has all been calculated using, of course, appropriate correlations. And by the way, it has been calculated for the same surface area. And the point, why is that the case? It's quite easy to explain. In the conventional fixed bed, the heat transfer is mainly dominated by convective heat transfer. So the convection plays a major role, while the POX perform very well also at low flow rates because they have a considerable contribution of the conductive heat transfer, so the conduction. And this is also apparent if you now would change the solid bulk solid material from Inconel, for example, to aluminum or even copper. Our material scientists were able to print also copper reactors. Then you see that, of course, the range where the POX perform better gets larger and larger. So this is, let's say, the influencing parameters are the solid matrix bulk material and also the superficial mass velocity. besides trivial parameters as porosity, obviously. I mean, the more solid material you have, the better the conductivity, but this is true for all cases. So now we want to see how does this now influence the reaction. And if we go into a reaction, we selected the methanol partial oxidation to form aldehyde according to the Formox process. And here, this reaction network is already, let's say, it's quite optimized. So the industrial reference process has a quite high conversion and selectivity, but still you have some CO as a byproduct, which you try to avoid. And as we all know, I mean, the reaction to CO and also to CO2, obviously, they usually tend to have higher activation energies. This means they kick off if you have a hotspot. So our working hypothesis was here, if we can now manage the temperature profile to be more uniform, we can also suppress the undesired CO formation. And this is shown on the next slide now. Here on the right-hand side, you see the two compared systems, which were compared in the experiments. So it's not only a simulation study, but also experimentally. You see here the particle system, and you see here the POX system, and both systems have the same catalyst mass, reactor volume, and the same conversion. And now the question is, how does the temperature profile look like, and how does the CO selectivity look like? And if you compare this, you see that for the POX, well, let's start with the conventional fixed bed. Maybe you see the typical hotspot here evolving here due to the exothermicity, and then due to the cooling, you get the temperature down again. And for the POX system, you see that you have a very flat temperature profile. You can really work nearly isothermal. And this cuts down the CO formation by half. So quite interesting result for this gas phase management, heat management in gas phase reactions. And now we also wanted to look into the, let's say, possibilities for gas liquid applications, so multi-phase operation. And in order to do this, we first did some studies on the liquid distribution. And if you look at trickle bed reactors, we have usually a certain liquid distributor. So this is a cold flow setup, and these structures here are polymeric nature, created by filament deposition, FDM technique. And what you see here is basically you have a liquid distributor, then you have a packing consisting of different stacks of different unit cell type geometry, and also sometimes the wall is printed directly to the structure and sometimes not. And then the most important thing is the liquid collector here at the bottom, with 21 collection zones of equal area. And then the liquid flow is monitored here automatically, so that we can know if at the end of the bed, basically, we have a nearly even liquid distribution, or we have some dry areas or some rivulets that form. And if you now compare two different cell types, Kelvin cell POX and diamond POX, you can see different patterns in terms of liquid distribution. What you see here is, let's explain first the scale. The scale means red is full liquid and white is only gas, and in between is a mixture. You see the liquid saturation basically. And here you go down the reactor column, and you see that for the Kelvin cell, at the end, you more or less have in the core of the packing the liquid, while in the diamond cell, you have at the end more or less, you see it here at the outer edge of the packing the liquid, and in the center you have dry zones. And you can explain this already by the unit cell geometry. And this brought one of my PhD students, Markus Lemmermann, to the idea of combining these two cells. So he created a new cell type, which we called diacal, because it's a diamond part and a Kelvin cell part attached to each other. And then by 3D printing, he created a full structure, 3D structure out of this unit cell. And then he compared the performance of the liquid distribution. And you can also express this by the maldistribution factor. If the maldistribution factor is 0, then you have a perfect even liquid distribution. And the higher, the more uneven the distribution is. And if you compare this with a reference trickle bed reactor consisting of spheres as a benchmark, and then you compare this to this POX consisting of the diacal structure, you see the blue line here, that in the beginning it's more or less the same because it's mainly influenced by the liquid initial distribution of the liquid on the top of the column. But you see that the liquid distribution in this POX structure gets better and better downwards. And you see this also visually here because you have a quite nice, even light red color. So improvements up to a factor of 2 could be achieved with the optimized design of the cell geometry here. As a test reaction for this trickle bed gas liquid application, we looked into the trickle bed system, which we wanted to avoid. Let's say, put it this way, that we have overlapping effects. We wanted only to look at the liquid distribution, and we didn't want to have an influence of too much of the reaction exothermicity or so. And this led us to a reaction system which is a hydrodesulfurization of crude oil, of diesel oil. And as a model substance, we used DBT for this. So the task here is that you have to come down from approximately 1.5 to 3% sulfur down to 10 ppm of sulfur components by adding hydrogen. So you create H2S and you desulfurize then your crude oil. This means basically this reactor is more or less a cleaning unit, and you really have to avoid any bypass effect because you need to achieve 99.9% conversion in this reactor, while the exothermicity is negligible because you only have, as you see here, 2% or so in the whole mixture. So, and in order to do this, you need then obviously go back to the metal substrate system. So we create first this POX as shown here. So this is the bare structure. In this case, we used a titanium aluminum alloy for this. This is the bare structure, and then you need several coating and impregnation steps to get the catalytically active substrate. The first one is your coating to get this aluminum oxide, and then you have an impregnation step with a cobalt molybdenum salt solution. And this precursor here needs to be activated, and the activation step is a sulfidation to achieve the cobalt molybdenum sulfide. And this substrate here is then put into this reactor. This is approximately a 1.5 meter reactor, and here then the reaction was performed. And what we could then see is that, in fact, if you relate the conversion to the catalyst mass, much better efficiency could be achieved in terms of conversion per used catalyst mass in the reactor. Coming from the POX to the inter-POX, in my title I have mentioned optimal and flexible reactors, and here I want to address the flexibility aspect a bit. So usually we talk about a POX consisting of a unit cell, cubic or Kelvin or diamond unit cell. But then one of our PhD students, Yang Do, came up with the idea of creating a so-called inter-POX, so an interpenetrating POX system. These are basically two diamond cell POX that are interpenetrating, but they are not connected to each other. And this enables you to shift the relative position, so basically the spacing between the struts of the two POX. Yeah, and I have illustrated this here. If you now look exactly here to this, where my laser pointer is, and I click here, so you see now this can be moved. Yeah? Now you have to think, of course, in larger scale system, but the one POX, the light green POX, is fixed, and the dark green POX can be shifted relative to the other. And the shift, the offset, can be defined by the distance between these two and these two struts. So this means basically if you have an offset, we defined an offset of 50%, then it's exactly this arrangement. It's equidistant is 50%. And if you now shift it, then you have an offset of, for example, 75%. And now this gives you some possibility to tune the reaction and transport behavior of the system. And we did this in a lot of detailed simulations, which I obviously will not show in detail. But what was done was a CFD simulation and a mass transport analysis. The mass transport analysis, I only want to highlight a new code development. And this is a distract foam solver, which is open available. So we have published this paper And we mentioned this solver there. You can use it to determine the dispersion coefficient and residence time distribution and so on and so forth. And it can be fully implemented in the OpenFOAM package. If you're interested in using this, just drop us a mail and you can have it. It's for free. And it enables us to determine this dispersion behavior of the system. Now, today, I want to highlight a bit the reaction control aspect, and I will just briefly highlight a short example on this. Because the question we had is, can I use now this offset position, so the relative positioning of the two structures, in order to influence the reaction? Yeah? So basically, influence the reaction not only by temperature and by concentration, but influence it by the geometrical arrangement, and this is important, by keeping the same porosity, basically the same system periphery, right? It's just the internal structure which changes. And in order to have a look into this, the first thing we did is we used the catalytic foam solver from Politecnico di Milano, from the Maestri group. And we used the CO oxidation as a case study using the Chemkin model from the Deutschmann group from KIT. And then we compared basically for the same inlet conditions, but for different offset positions, we compared the concentration profiles and the conversion. And if you have a look at this figure, you see that there is a difference. You also see that the difference is not so large here. The reason being that the CO oxidation here is quite fast reaction. But you see distinctively, you see that the CO concentration remaining is higher for the 75% offset than for the 50%, and correspondingly the product concentration is lower. So this means you have a lower conversion in the 75% offset. And this gives you now some possibility to adjust the conversion of a chemical reaction. And if you do this now for a system reaction that is not so fast, we did a model reaction A to B here, you see that the difference in conversion can be up to 12% absolute, and relative it's even higher percentage. This means depending on the reaction rate and the transport properties, you can tune the reaction behavior, having the same geometry, having the same inlet conditions, but you have basically a kind of a windshield effect here in the structure. So this strut covers this one, and this means the surface area available for the reaction and for the fluid flow is lower, and this is a reason for the lower conversion in this aspect here. With this, I'm at the end of my talk. I want to summarize. So we have seen that POCs are an interesting option for process intensification in catalytic reactors. We have seen that for heat management, they're quite favorable, but also you have always to see in which operating range you operate your reactor, but it has a superior heat transfer performance. In gas-liquid applications, you can enhance the gas-liquid distribution, and you can also therefore manage trickle bed reactor operation more efficiently. And finally, the interPOC system is a quite interesting newest development where we can try to, in operando, basically adjust the geometry in order to tune conversion and also the heat release in these reactors. And with this, I'm at the end, and I thank my team. And I thank you for your kind attention, and I'm looking forward to your questions. Thank you.
Thank you very much, Hans-Jörg. Excellent presentation. I think that it is an issue of big interest. And so time is open for questions.
Maybe I can start. So Hans-Jörg, many thanks for this very inspiring talk. I really liked it. Question, this experiments on the liquid distribution, was that with water or with an organic liquid? Or actually, how is he, so is he
Yeah, I understand your point. So we did it with different configurations. You're addressing a very important point. It's also it's not only the liquid that is important, but also the printing technology. Because if you use filament deposition, you get a rough polymeric surface, and this is more, let's say, similar to the real metal catalyst support. While if you use a stereolithographic technique using a resin, then you get quite smooth surface. and then you are probably quite off the, let's say, real results in your metal system. And we used both, actually. We used water, but also we used other mixtures, and we measured contact angles and so on and so forth. It's the matching of the two, of the liquid and the solid.
Okay, thanks.
For my part,
I have also a question.
Sorry.
Hi, here's Jan Kopyczynski, Montreal in McGill University in Canada. Thanks so much, Hans-Jörg, for the nice talk. Are you able to 3D print essentially structures? Let's say at the beginning they have maybe a higher porosity and towards the end is tighter porosity, or vice versa, maybe to counteract maybe as a pressure drop, or maybe even have a larger catalyst loading either at the beginning or at the end?
Absolutely. Very, very good point. Thank you for that question. That is just, let's say, ongoing work really to optimize, based on rigorous optimization, really to optimize the distribution. You can nicely do that, as you mentioned. You can, for example, in the beginning, where the concentration is high, you can go to higher porosities, lower catalyst inventory, and then at the end, where you want to achieve the rest conversion, you can get more catalyst. You have this degree of freedom in the 3D printing of the structure, and then later on, of course, you have to do the coating step in addition.
Yeah, follow up, what was the resolution for the printing? Maybe you mentioned it, but maybe I forgot. In terms of, it's like 10 micrometers, 20 micrometers, or 100 micrometers?
Yeah, it's a bit, the resolution of the strut depends on the metal powder you use. Usually the metal powder is in the range already of 30 to 40 microns. Otherwise you get what the material scientists call dusting. And then you have to think like you need a few metal powder particles, in order to get a reasonable strut stability. So we are talking more about here macrostructures. We are talking about strut sizes, let's say definitely above 100 microns. Rather, let's say 300 or so. But there's also other 3D printing methods that can go to lower resolutions, but we don't do this.
Well, thanks so much. Maybe I will contact you. Maybe you can send me some to Canada.
Sure. Yeah, sure.
Okay.
It's my pleasure.
Danke. Bye-bye.
Hans-Jörg, please, could you comment briefly on a comparison of these structures with open cell foams?
Yeah, actually, the open cellular foams have very similar properties in some of the regards I mentioned. Yeah, they're also an interconnected strut network. The reason why we went to 3D printing is that you really have the full control on the morphology. And in this open cell foams, you have this replication technique in the manufacturing, and sometimes, so you don't have always the even strut size, and sometimes you have blocked pores and these kind of issues. And therefore, we moved on from this open cellular foams to this POX. But they share some of the advantages, definitely they have in common.
Okay. Thank you very much. We don't have more time. So thank you, Hans-Jörg.
Thank you. And if you have further questions, just drop me an email.
Okay. Our next speaker is Professor Paul Dauenhauer from the University of Minnesota in Minneapolis, and also from Catalysis Center of Energy and Innovation in Newark, USA. Professor Dauenhauer's research interests are related to the development of sustainable energy technologies. His research aims to address the catalysis and reaction challenge associated with renewable and new carbonaceous feedstock to the fuels and chemicals of tomorrow. The invention of new experimental methods combined with new catalytic materials allows him the development of the new generation of energy technologies based on a detailed understanding of chemistry. His publications focus on catalysis and chemistry of highly functional renewable starting materials, mechanisms, and kinetics of complex reaction systems and reaction transport interactions in new macro-mesoporous materials. Focusing on active system on a scale from catalytic active center to particle to reactor allows Professor Dauenhauer to utilize the fundamental knowledge to industrial applications and really increase the opportunities for collaboration with industry. Well, the Title of the lecture is Dynamic Catalyst for Renewable Energy and Bio-Derived Materials. They are also co-authors Ardak, Sedi, and Abdelrahman. So please, Professor Denhauer, the floor is yours.
Thank you, and thank you to the committee for organizing this and with the complexity of doing this online. I want to talk to you today. We have a bit of time. I want to have a new audience, which I appreciate. A lot of people I've not met, which is unfortunate. I hope to meet in person, but maybe in the future. But I wanted to show you a new idea we've been working on the past couple of years that I think could play into some of the things we've been talking about in the earlier presentations. Can you see the slides okay? Okay, I'll proceed. Okay, so let me, you can, okay. So let me proceed. Let me just get this out of the way. I have equity in these companies, and I'm required by the university to disclose that I have all of this, but it shouldn't matter for this talk. So if we go back to what was talked about earlier by Professor Marin and others, we have a large challenge ahead of us to meet our goals by 2030 and 2050 for climate change. And of course, what's changed amazingly in the past 10 years is that wind and solar power have become amazingly cheap, making the use of low-cost carbon neutral or carbon negative electricity of an economically viable source. And what we would like to do with that then, of course, is use that for the purposes of energy storage, energy utilization, carbon capture, etc. And of course, all of this comes down to the idea that we have power from wind and solar to use things like water, CO2, and air to make molecules like hydrogen, ammonia, and methanol. So these key energy reactions, of course, are traditional classic problems in both catalysis, reaction engineering, and reactor design, in addition to process systems. And the problem has been, why haven't these matured more in the past 30 years, 40 years with a lot of effort into them? And if I summarize everything in the most basic idea, they all come down to one problem, which is they're all limited by the Sabatier principle. Of course, this is a well-known idea that's been talked about by many others before me, but the idea being very simply, if I look at a lot of catalysts for ammonia synthesis, a few catalysts that were discovered 100 years ago sit near the top of the Sabatier volcano peak. Same thing with methanol synthesis. Copper zinc oxide is now one of our best catalysts for methanol synthesis, but this also sits near the top of the peak. And for oxygen evolution, if I look at the metal or metal oxide volcano peak, of course, oxygen evolution is important if I'm going to convert water into H2 and O2. Catalysts there also sit near the peak. And at the same time, these are logarithmic plots. I would like to exist 2 to 3 orders of magnitude above that peak. Now, of course, the goal is to find materials that don't exist on these Sabatier volcanoes. And of course, if we find that, that'll be a wonderful breakthrough. But I want to take a different approach and think about this differently based on the ideas of where these volcano peaks actually originate. So let me just back up. If there's students here that aren't familiar with this concept, it's important to what I'm going to show you. So let me just summarize this quickly. Of course, the idea of a catalyst is we take a reactant and we make a product, and that goes through some high energy transition state. The alternative being, if we adsorb the molecule first to a surface, we can achieve a transition state that's lower in energy. And then this comes off the surface, I could potentially get a lower barrier. But in the act of lowering the barrier on the surface, I introduce new barriers, one of them being, for example, the adsorption energy. So in this case, I might speed up the reaction, but I slow it down by desorption. So a better catalyst might look something like this, right? In this case now, the energy of the reaction is lower than the transition state in the gas phase, and my desorption barrier matches my catalytic barrier. So in this case, desorption is comparable to reaction. Well, let's say I wanted to go even faster, an even better catalyst. What could I do? Well, at this point, what I could say is, well, let's see if I can find a material that gives me an energy barrier that's lower on the catalyst. But what you see is that then by the linear scaling relationships of this reaction, a more exothermic surface reaction does lower my barrier here, but it increases another barrier, which in this cartoon depiction is the heat of adsorption. And this comes to this basic idea that at some point there's a limit to how much catalyst can be improved. Once I've improved them up to this optimal point, the trade-offs of improving one step affect the limitations of another step. And this basic energy idea is the origin of the Sabatier limit. So if I come back to this picture, every reaction has a series of steps. In this case, the simplest cartoon, adsorption, surface reaction, and desorption. I can think of a trade-off in these steps where I optimize the catalytic material to balance those two. So the descriptor here on the independent x-axis is a description of the material itself, and the vertical axis here being the overall rate, the turnover frequency. When I go between different materials, I switch between which of these elementary steps is rate limiting. And eventually I can find a material that balances these two nicely. And that's this optimum you see right here at the volcano peak. Now, like I said, what we'd like to do, though, is exist up here above, orders of magnitude above, that give us higher rates for hydrogen production, methanol synthesis, ammonia synthesis, and hundreds of other applications. And in this case, if I can't get off of this volcano curve, I can't create materials that exist there. Now, what could we potentially do about this? Well, one idea is, let's, instead of finding a static material, right, a metal or a metal oxide that sits at one of these description points, let's find a material that we can actually change with time. So I'm going to change the electronic characteristics of this material such that I move left to right on this descriptive scale. Now, if I'm doing that, what I'm essentially doing is switching from one condition of rate limitation to another. And if I do this fast enough, the prediction was, when we started this, that we could actually exist on these rate limitations up above the static optimum that you see right here. So this is the basic idea of what I want to present to you here. If I oscillate a reaction at the frequency which matches the natural frequencies of the independent elementary steps, I can achieve this resonant frequency, which is orders of magnitude above the Sabatier peak. Now, of course, there's a lot of things that go into this. This is a relatively simple reaction. There's an amplitude I have to pick here. There's a structure to this waveform oscillation I'm going to apply to a catalyst. There's a frequency, but also I care about how to do this in real systems with real devices and real chemistry, which are multi-step. So let me proceed. What's actually happening when I change a catalyst with time? Well, if I think about a catalyst in one state, I have, of course, for the simplest system, adsorption, reaction, and desorption. And when I change the electronic state of that material, I now have a new energy diagram. So I go from state 1 to state 2. And of course, if each of these are favorable for one elementary step, right, you can actually see that, because from going from side to side on a volcano, you can actually see which reaction step that's favorable for. So state 1 here gives me the lower energy barrier for the transition state surface reaction. And state 2 gives me more favorable desorption. So if I'm flipping between these two, I'm going to increase the rate of each of those elementary steps independently. That's the basic idea. It's rather intuitive when you see it put together for such a simple reaction. Of course, this gets complex when we start talking about more complicated systems. Now, how is this different than what's been done in the past? Because, of course, dynamic reactors and systems have been studied for over half a century, or perhaps even longer. And there's been a lot of good work in understanding how temperature, pressure, composition, heating, cooling, co-reactants, all these kinds of things matter. Now, of course, you can break down the dynamics of chemical systems into two groups: the passive changes that happen without us forcing a system. So, of course, catalysts activate and deactivate, reactors become unstable, and processes become unstable. But in this case, we're interested in forcing the catalyst to change between two different conditions, in which case I'm interested in this top row. Now, in system dynamics, for system dynamics, we look at things like chemical looping or catalyst cycling. For reactor dynamics, we're thinking about changing the temperature, pressure, composition of the reactor. In this case, what I want to do is I actually want to go to the catalyst itself, the active site, and change its electronic characteristics, or change its sterics or its physical structure with time, or both. So what happens when I do this? So let's look at those top left two boxes. In the system we're interested in, I'm going to change the catalyst itself. So I'm actually changing its energy diagram with time. So what happens is each of my binding energies are moving up and down in binding energy of the surface reactant A star and the surface product B star, but also my transition state energy is changing because the relative energies of the surface reactant and surface product are changing. Now, if I'm keeping the temperature constant there, you can see that I have the thermal energy to go over the barrier under certain conditions and not at others, and I have the energy to get off the surface in certain conditions and not others. This is very different from a condition where I have a fixed catalyst and I'm oscillating the temperature with time. It gives me different behavior overall. Of course, this is a very interesting system with a lot of potential, but there's some key differences. Number one is if I'm oscillating the temperature of a reactor, I have to get incredibly small to get reasonable kinetics, because I'm not just heating the surface, I'm heating the particle to support the reactor walls, etc. So the benefit of a dynamic catalyst, for one, is faster kinetics. So when I say this, I'm interested in turnovers which are above 10 turnovers per second, really fast reactions. And to do that, I need system dynamics that are sufficiently fast, which I can do with electricity and not with heat. It also gives me better molecular control, because in this case, dynamic catalysts can affect different elementary steps, but also different adsorbates with time. Okay, so let's imagine I'm going to focus on dynamic catalysts. So how do I think about how these give me better kinetics? So which of these dynamic catalytic energy diagrams provide better kinetics? Because I can imagine if I have a catalyst and I want to perturb it electronically in some way, I can change this in all different methods of perturbation, which give me different changing energy profiles. So for example, the one on the left here, I'm going to explain what this is called positive gamma dynamics. And you can see that both surface intermediates move up and down together. They move by different amounts, but they move together. Whereas the one on the right gives me negative gamma dynamics. The two surface energies of the surface reactant and product move in opposite directions. So of course, which one gives me better performance, but also how do I define these dynamics so I can think of global analysis and optimization of dynamic catalytic reactors. So let me take the simplest case and walk you through this. Of course, if we have a simulation of a catalytic reaction, let's take the simplest case first. Let's take a perfectly mixed flow reactor. I have my reactor parameters, space velocity, temperature, and pressure. I have my catalytic chemistry parameters, so the overall thermodynamics, the heats of adsorption and transition state energy. But now I have new parameters that I have to account for. So in this case, I'll have the amplitude of my oscillation of that catalyst. I'll have the amplitude position, the frequency, and the waveform type. And so this makes the system immensely more complex, even for a simple A to B surface reaction. Okay, so what does the simulation look like? Let me walk you through this. If you just take the top line here, this is showing you the binding energy of one of the two surface intermediates, B star. And what you see is that it's going from strong binding to weak binding with time. It's a square wave. So I go from one state at strong binding at 0.5 electron volts relative energy to negative 0.1. So these are all negative enthalpies of adsorption. But this is a relative binding energy, which is why this number is positive. But don't worry about that. This is strong binding, weak binding, strong binding, weak binding. Now, when I do this, I'm changing the surface coverage of the catalyst. So if you come down to the very bottom graph here, what you can see is that if I have an A to B reaction, my surface goes from covered in B to covered in A to covered in B and back and forth. And every time I flip the catalyst from strong to weak binding, I'm removing all this B from the surface, and you can see the rate goes up into the 15 to 20 turnovers per second range instantaneously. And then as I deplete the surface, the reaction rate actually comes back down. I refill it, and I'm essentially filling the surface and unfilling it back and forth, back and forth. So what's happening here is I'm filling its surface and then unloading it as a product. And so it matters how fast I do that. So what you're looking at here is this instantaneous turnover frequency is the vertical axis. And the horizontal axis is the simulation with time. Of course, if I'm doing this at different frequencies, I'm going to show you this as an arbitrary x-axis so I can look at many frequencies at once. So if I'm doing this really slowly, every 1,000 seconds, I flip the surface between its two states, the system behaves like two independent catalysts. So for example, I have a very slow condition and a moderately slow condition. And the only benefit I get is when I flip the catalyst between these two states. So here you can see this overshoot. This is not an artifact of the simulation. This is that benefit I get from flipping the surface. And you can see it's negligible in the overall performance. If I increase from 0.001 hertz in green up to 0.25 hertz in red, now what I'm achieving is the same turnover frequency as I would get in the best case for a static catalyst. And you can see I'm flipping the surface. I'm giving this instantaneous benefit of flipping, and then I slowly deplete the surface and I flip again. If I flip even faster, I go up now to 10 hertz, I'm achieving catalytic rates which are an order of magnitude above the Sabatier peak. And you can see I'm not depleting the surface with time before I start refilling it again. And if I go faster and faster, I can actually fill and unfill the surface even faster at 1,000 hertz and go up about another order of magnitude in time averaged rate. Now, how fast can I go? Well, it turns out that I can't go faster than the elementary steps of any particular state. So if I look at a frequency response plot, it can actually tell me when I reach this resonant condition. So here is on the bottom axis is the frequency at which I'm flipping my catalyst state between two different conditions. You can see I'm covering 16 orders of magnitude in frequency. So very slow. Here's 1 hertz right here up to insanely fast frequencies, which are not even attainable up there, 10 to the 12. My best case scenario that I could get for a static material is right here in red, the static optimum. And what you see is that I start out very slowly under dynamic conditions. I behave like 2 very slow catalysts. And once I hit this corner frequency, I increase in a 1-to-1 linear relationship between the applied frequency and the frequency I get out of the catalyst. And eventually I keep increasing to the point where I meet the natural frequencies of my catalytic elementary steps, and I can't go any faster. At this point, I'm filling and unfilling the surface, and eventually I can't even fill and unfill the surface anymore. I'm too fast for my elementary steps. So this gives me this incredibly fast catalytic rate, but there's a band of frequencies which match the natural frequencies of my reaction. So that was for one amplitude. That was for 0.6 electron volt oscillation in B star. So you can see that right here. If I had taken a vertical line up here, I start out very slow. I increase, I hit this plateau in high rate, and then I go back down in frequency, catalytic reaction turnover frequency in the top part here. But if I'm moving left to right, I'm changing the amplitude of my reaction. So bigger amplitudes give me higher catalytic rates, to the point where if I can get incredibly large amplitude oscillations, I can get oscillations that yield turnover frequencies that are probably beyond the diffusion limits of my particular system. So that's good. If I want to improve catalyst performance, I want to increase the oscillation amplitude of my particular catalytic reactor. Okay, so one question I always get, and I want to put this right up front, is if I'm spending this energy to take a catalyst and flip it between 2 states, how much benefit am I getting for that particular system? So every time I flip the catalyst over, am I turning over the reaction itself? And so I can define a very simple turnover efficiency as my dynamic turnover frequency divided by my oscillation frequency by subtracting off the steady state turnover frequency. So what you see then is this turnover efficiency in the right here in color. So 0 means every time I flip over the catalyst, I put in that work to do that, I don't get any benefit in terms of catalytic rate. 100% means every time I flip the catalyst in between states, I get a catalytic turnover, which is what I want. So what you see here, if I look at the frequencies and I look at the oscillation amplitude, there are conditions here which give me incredibly efficient catalytic reactor performance. And you can see here, this even goes up into the high 90s, where essentially every time I flip the catalyst over, I'm getting this benefit. This is the region where I get a 1-to-1 relationship between catalytic rate increase and frequency at which I apply to that particular surface. So this leads right up to the start of the resonance band that we see in the frequency response plots I was showing you earlier. So it is possible for these systems to be incredibly efficient, but you have to pick the right conditions. Okay, so of course I've shown you this for one chemistry, but I'm interested in taking this and applying it to complex mechanisms with all sorts of different parameters. So a very important relationship is if I have 2 molecules on the surface connected by a transition state, is that transition state energy is related to the energy of the surface reactant and surface product. And one way to describe this is a simple linear relationship. So the activation energy here scales linearly with the surface heat of reaction by 2 linear scaling parameters, alpha and beta. And of course, if I change alpha, I'm changing this transition state energy, which means I'm changing one of the elementary steps in my two rate limiting phenomena. And if I'm doing that, I'm changing the shape of my volcano here, as you can see on the left. So I care about understanding these systems globally in terms of what do the linear parameters of every single elementary step relate back to my dynamics. There's actually a very simple way to think about this. I have different volcano plots depending on these parameters, but I also have different inverted dynamic volcano plots you see up here on the top. And you can see that the ones with the sharpest slope, of course, in the normal volcano, give me the sharpest slope in the inverted volcano. And that's really important because if I go to the next slide, I can imagine, for example, a system with an alpha of 1. This is the sharpest volcano you can get. In this case, here's my conventional Sabatier volcano. Here's the peak. And you can see the inverted volcano on the top where I now have my tie lines connecting different amplitudes of oscillation. Now, the sharper the volcano, the higher the alpha, allows me to achieve higher frequencies by looking at higher amplitude oscillations. So if I oscillate a catalyst at higher amplitude, it's pushed up to higher potential resonant frequencies. And you can see that over here on the plot on the right. This resonance band of conditions, if you look at the inset for 0.6, 1, and 1.5, goes up to incredibly high rates that are way beyond the diffusion limit of any particular system. Of course, these are for incredibly high non-real amplitudes, but the idea is to show you what the benefit of different types of chemistries are. If I decrease alpha, if I back up, I'm going to get shallower plots and I'll get less of a response to dynamic catalytic systems. So every chemistry, of course, has different performance. So I'm interested, of course, in all sorts of different catalytic reactions. So what I can do, I was describing the linear relationship for the transition state. I also care about the transition state, or the linear scaling relationship for A star versus B star, in which case B star here moves a lot more than A star, and I can relate those also by a linear relationship. So that's my gamma parameter. And if I change the gamma parameter, now I'm also changing the shape of the volcano, and that gives me different catalytic performance. So I was showing you earlier different gamma values. I showed you a high gamma value originally, and I'm not even showing the negative gamma plot on here because that just adds more complexity. But of course, each of these linear scaling parameters gives me different volcano shapes, any of which I can oscillate in a different way and give faster catalytic performance. So here's the full plot all together. Now, how to do this? Now, I don't want to go into this, but I want you to see that there are ways to actually implement these types of systems, whether through dynamic strain, photocatalysis, electronic gating, catalytic diodes, ferroelectrics, electrocatalysis. There's many, many ways this can be done. We're pursuing several of these, and other people are pursuing other methods. The whole point is to convince you and show you that the benefit of doing these types of dynamic catalytic approaches gives you rate control beyond anything we have right now. Okay, what else? Let me end by showing you a couple of other benefits that exist in these particular systems. If we look at the ammonia system or the methanol system, one particular problem is thermodynamics. If I think of a reaction from reactants to products, I want to push this forward. What I need to do is change the overall delta G of reaction. And the way we do that right now, for the most part, is we apply work ahead of time to shift the pressure or temperature or both to give me a more favorable reaction. And so for something like hydrogen compression, this is a huge cost, both in work, operating cost and capital cost. And so one benefit we get from going to a dynamic catalyst is we can put that work directly into the surface. So instead of putting the work into a compressor or some high capital approach, we can actually keep the overall thermodynamics of our system and apply that work directly to the catalyst surface itself. And when we do that, of course, we're not changing thermodynamics. We can't change the laws of thermodynamics, but we can apply extra work in an open catalytic system that changes the steady state away from our equilibrium state. Now, let me show you how this actually looks in a simulation. So what I'm showing you here is a batch reactor. This is my time on stream on the x-axis. And what I'm going to do is I'm going to start my batch reactor at multiple initial conditions. This is an A to B reaction. I can start it with pure component B or pure component A. And when I let this run with time under dynamic conditions, you can see that no matter where I start, I go to this new steady state you see right here, which is different from equilibrium. And then when I remove the dynamics, I'm no longer putting work in through the catalytic surface. The system, of course, has to, by the laws of thermodynamics, go back to equilibrium. And if I turn this back on and off, it'll go from the steady state to equilibrium. Now, why is this possible? This, of course, occurs because I'm putting in work through the surface, and that occurs by this energetic ratchet mechanism, which is known throughout biology and many other places. Now, why does this work and how does it work? Well, I can push a reaction. What you're looking at here is a steady state conversion. Green is equilibrium, red is high conversion, and blue is low conversion. So if I let a system oscillate at low frequency, it goes to equilibrium. At high frequency, I can push it forward or backward, depending on the conditions and catalyst that I pick for my particular application. And I can understand why this is such a nice dividing line, the very simple interpretation of the dynamics of my particular reaction. So there's a very simple cartoon here that allows you to understand what's happening. If I look at the right side, under the forward driving system, if I'm pushing something past equilibrium, I have these molecules here at higher energy or higher binding energy, so lower overall enthalpy in the strong binding condition. And then when I flip to the weak binding state of my catalyst, these come off the surface. The reverse is true in a catalyst that drives reaction backwards away from equilibrium. On the strong binding conditions, my surface reactant is stronger binding. And that's why I get this very simple dividing line between forward and reverse reactions. So where are we going with this? I'm going to end here with this last thought, which is I want to take this to real systems, and I want to do that with real devices, which we're working on in the lab. I want to continue to build the theory of understanding these different energetic mechanisms for catalysis, but I also want to take them to real chemistries, and that's the work we've done here with Professor Vlachos at the University of Delaware in the United States. You can read about this in a preprint, where we've been looking at the effect of dynamic strain in ruthenium catalysts for ammonia synthesis, and in which case I no longer have one elementary step. I have multiple pathways to form ammonia from both hydrogen and nitrogen, and understanding how the rate limitations change as I dynamically strain the system at different frequencies and oscillation amplitudes completely changes the rate at which I can synthesize ammonia. So let me leave it here. The most exciting element of this to me is that it's no longer a search for a material, because historically catalysis has all been about finding a material and then making it work within a reactor system. In this case, it's a strategy. I want to combine chemistry, perturbations, and materials that allow me to build, optimize, and test systems to get beyond the Sabatier peak, to push reactions past equilibrium. And the benefits here are potentially very large. And of course, the targets are the things we care about for energy: hydrogen production, methanol synthesis, selective oxidation, ammonia synthesis, etc. So let me leave it there. I appreciate the organizers inviting me, and thank you all for either getting up early or staying very late.
Okay, thank you very much, Paul. Very, very nice presentation that shows how to connect the atomic scale and the real world operation of catalytic reactors. Then it's time for questions.
Can I ask the question, please?
Okay.
Hello. Thank you very much for a nice presentation. It's amazingly fantastic theoretical analysis. It is great, really. I have the following question: is when you select some resonance parameters, is it sensible to reaction mixture composition? I can prolong that. For example, when you are dealing with a small reactor, it's maybe easy, but when you are dealing with a commercial reactor where the composition in the inlet part and outlet part are absolutely different, so is it possible that these oscillations will work differently in different parts of the reactor?
I think that's a great question. Yeah, the answer is likely. For many reasons. I'm going to change the composition, which means I'm going to be changing the surface coverages on my surface. And that's going to be, as you saw in the very first simulation, the surface coverages matter quite a bit for the dynamics. So if I imagine reactors, let me back up to all the different ways this can be implemented. I can do this quickly here. Come on, let's go. What I think you're getting at is the waveform I apply to a catalytic reactor would have to be different in the beginning, the middle, and the end of the reactor. But of course, if we have electronic input, we can do that. I can give it a gradient of oscillations. That's a great question. Actually, you're the first person to ever ask me that. I've never even thought of that. So thank you.
Okay, thank you.
Okay, more questions? Well, it seems no. And well, thank you very much for attending this session, and I think we can close it. So thank you very much to everyone.
Thank you very much. Bye-bye.